Okay, to people just joining us, we are doing a first look at Jonathan's category theory framework, and yeah, take it away. Where do we start?
Okay, right. I'm assuming you can still see this blank.
I can see a blank notebook. So far, okay. we're just. What is it? It's the non-category. What is the empty category?
Yeah, usually it'd be called a null category.
Okay, fine.
The object set and the hom set are both null sets.
Okay.
Okay. So to begin with, it's probably easier, rather than going and introducing categories straight off, it's probably easier if I introduce quivers, which are sort of the structural basis of all categories in the framework. So we have this function abstract quiver, where, I mean, there's a bunch of different ways you can call it, but probably the easiest is you just pass it an association of arrows and objects those arrows connect. So then say full labeled graph. So this would be a quiver, right? And
hold on. Go ahead.
So wait, sorry, is the right-hand side of each of those rules, does it have to contain exactly two things?
Yes, so every arrow has to be a binary relation. It doesn't actually have to be, it doesn't have to be a list, it can be anything, these could be directed edges or whatever. But
I see. Is there a reason? I'm just wondering if there's a reason that, like, if this could also be done using tagged directed edges.
So with these graphs, that's exactly how it's being done. And so it's important to note that abstract quiver can accept graph objects. So if you pass it a directed graph, it will work.
I see. So just as a matter of syntax, you could have given it a list of tagged directed edges instead of that association there?
Yes, exactly. And when you pass it a graph, that's exactly what it's doing.
Sounds good.
Constraints on the quiver, or is it just any collection of arrows?
Any collection of arrows. There are no constraints. And so, quivers are effectively directed multi-graphs, so you could have multi-edges, you can have self-loops. There's no constraint on what you can do with these. Mm-hmm. And obviously, so these are, I should just note, obviously quivers are like mathematically interesting structures in their own right. They come out of representation theory. They get studied in the context of Morita embedding and those kinds of things. But the context in which they're relevant for us is that they provide the underlying structural basis for a category. So the reason why they're called quivers is because they are collections of arrows. They are effectively categories where you don't have composition and you don't have identity. And I should
wait. Let me just unparse that thing. There are collections of arrows where, say that again.
So it's just a collection of arrows. So a category is a collection of arrows, in effect, a quiver, where you have this binary operation, which is composition, and where you have identity maps.
Okay.
So two arrows in a row is not composition?
No. So no, because if you take a quiver like this, right, the fact that there are two arrows in a row doesn't guarantee that there's an arrow from X to Z. Whereas if this were, or X to Z, if this were a category, it would. So in fact, okay, let me.
Right. So categories. I mean, these are just graphs, and categories are transitive graphs where everything has a self loop.
Right. Okay.
Right.
So they're transitive. So if I now show this, if I give it the underlying structure of a quiver, this is what you get. Exactly as Christopher said, you effectively get the transitive closure of this thing with self loops at every vertex. And so you've got G compose F that takes you directly from X to Z.
Cool. Okay. Hold on. This is all very beautiful. The only thing that isn't beautiful is the graphic design of these graphs, which I think could, and the fonts, which could do with a little bit of work. Sure. But that's very nice. Okay. Okay, I get it.
What are those X tilde? What's that?
Right. Okay. So those are the symbols for the identity morphisms.
Yeah.
So if we hang on, if I say, so those things can be overwritten. So if I say circle times and I say like over bar or something, that will replace the composition operation with circle times rather than circle dot, which is the default, and it will replace over tilde with over bar for the identity.
Are those the only optional things in an abstract category?
Oh no.
So if I wanted it, okay, this is just a super detail. Don't worry about it. But like that Z bar, often one see a 1 sub Z being the identity on Z.
Right. So I could do something like subscript
1 comma hash. 1 comma hash.
Yep.
I see. Yeah.
Which might be a better default. I don't
Oh, who knows?
I don't mind.
Right.
But no, okay. So Stephen, sorry, to address your question, I should say, I mean, this will become more relevant later. But so categories have lots of different options. So that you can see a category is defined by this association. So it's got effectively a collection. It's got an underlying quiver, which is this thing here. And it's also got a collection of equivalences between objects, equivalences between morphisms, and it has symbols for the composition and for the identity. So to explain these equivalences, perhaps it's easiest if I show that in the case of quivers first. So for something like this, if instead of saying full labeled graph, I said reduced labeled graph, then what I'm doing is I'm saying I want the labeled graph of this quiver modded out by a certain set of equivalences between the objects and the arrows. So I could have an equivalence between objects. I could say something like x equals y, and that would reduce the thing to this. So now f is a self loop effectively. And I could have equivalences between the between the arrows. So I could say g equals h, and I get that, for instance. And these morphism equivalences and object equivalences are the same idea, but now applied to categories rather than just.
Hold on. First question is, so the way those equalities are being treated is left-hand side is going to right-hand side. That's why the representative is y, not x.
Yes, exactly. And I'm not too dogmatic about which way around that. It felt natural to treat them as like an LHS to RHS rule, but I can also see an argument that the left-hand side should be the canonical element, in which case it should be.
Okay, all right, fine. But it's just my feeling is, I don't really know, but my feeling is it might be more natural for the left-hand side to be that, but it doesn't really matter. But the basic point is,
I agree.
The second argument of an abstract quiver by default is the equivalence between objects, and the third argument is the equivalences between morphisms. Is that correct?
That's correct. I mean, so again, if you want to be really pedantic, the actual structure is the quiver internally is an association of objects, arrows, equivalences between arrows, and equivalences between objects.
Okay. Out of curiosity, could you write the g equals f instead of g equals h?
Yeah. So that would now look like this, and it would be exactly the same.
Oh, like that. Yeah. Okay.
Wait a minute. Wait. How, I don't understand. G equals f.
Wait, but
why is
shouldn't that
right?
mean that shouldn't that mean that y equals x and z equals y or something? If g equals f.
Yes, but so what you've done is you've fed in an incompatible set of equivalences, right?
Right.
Well, I don't understand. I don't understand that. Hold on.
The domains and codomains of your equivalences don't match up.
Right. That's why I want to try that one, but I'm not sure I totally understand what the result is.
So this should throw an error. It doesn't right now. But
okay, fine.
This should throw something that says, domains and codomains don't match.
So you can only give an arrow equivalence if they're basically just multi-edges.
Well, or if they're multi-edges modulo other equivalences, right?
Okay, sure. Yeah.
Could you canonicalize it and add additional object equivalences to make the arrow?
Yes, yeah, you could, and so probably, actually, that's a fair point, right? We could either have the thing just throw an error that says these things don't match, or try to find the minimal set of object equivalences that would make make that set of the set of arrow equivalences compatible.
What would be the analogous? I mean, it's like a matrix multiply where the sizes don't match or something, where we don't go and try and search for compatibility. Are there other examples in algebra where we are, for example, where we are searching for compatibility? Roger, do you have a thought, or Jose, or anybody?
And think of one. I mean, I take that back. Okay, we do. We infer, like long time ago, we introduced like vector variables in ND-solve, and if you give the initial value, let's say that's a vector or a matrix, then we infer that the variable has to be a vector or a matrix of that dimension.
Right. So probably there's an option. Go ahead. Ian.
Threaded construct, where you specify how two arrays thread together.
Yes. What about it? I mean,
But
Yes,
but we
that's
don't
okay.
Seems related
infer
to,
there.
like, is it a scalar or a vector?
Right. Okay. So
This isn't a scalar vector problem. This is just a problem of you can give constraints, where it has to then figure out that they're, based on the arrow constraints, it has to infer that there are a bunch of object constraints, but there are different sets of object constraints that it might infer and so on, right? So it's, I don't see why this
it may
is
not
quite the
be
same.
unique.
Is the point that if you have
Yeah.
like X, you may want the X to represent a vector, but the X could stand for a list?
I'm not
I
sure.
don't think so. I think it's more just that you add one constraint and then there are multiple different. I mean, fundamentally, what's happening is, we're giving it, the arrows, and then we're giving it constraints, and it's giving some solution, some way of sort of identifying objects and arrows, so that that obeys the equivalences. And right now, my impression is that it's only doing that when there's sort of a trivial solution, right? When it's just like multi-edges and stuff like that. But if we allowed it to do more complicated things, then there might be many different solutions and stuff like that.
So
Right.
I should mention this problem. So this is treated in some of this functionality, just not directly at the level of equivalences. So like later on, when we look at sort of commutative diagrams and handling of groupoids and things, there are instances where we effectively have to return the minimal set of equivalences necessary to, say, make a diagram commutative or turn a category into a groupoid or something like that. And so in those cases, we just return a canonical set of equivalences that's known to be the minimal one. But obviously, in general, there would be many such.
Okay, let's move on.
There's actually, sorry, one last question is, so is there a reason why in the association representing the quiver, why does it have to store all the equivalences and stuff? Why doesn't it just bake it all in and then give a big set of arrows?
Oh, so okay, so because we want to be able to distinguish the full quiver from the reduced quiver. Now, for the particular case of quivers, it's not immediately obvious why you'd want to do that. Later on, when, for instance, we want to distinguish, say, epimorphisms versus monomorphisms or something, then it becomes important which morphisms are lost and which morphisms are preserved when one mods out by equivalences. So you need to know both structures.
I see. Okay, makes sense.
Okay, should we move on?
Sure. So again, like doing super basic stuff just to start with, it's obviously worth noting that obviously the formal definition of a category is something where you've got object morphisms, you have composition, and crucially that composition satisfies the axioms of associativity and the axioms of identity reflexivity, and that these self loops act as identity morphisms. So to show you an example of how that works. So internally, abstract category keeps track of everything that's being equivalent. So here you can see H compose G in brackets compose F. But if I say commutativity equations, associativity equations, associativity, it returns the minimal set of equations that it internally is storing to ensure associativity between these morphisms. And similarly, I could say identity equations. And it's returning the minimal set of equivalences needed to ensure that these self-loop arrows act as identity morphisms. So, F is equivalent to F compose X tilde, etc.
So are you literally computing all the paths, or?
To get out these equations.
You said you minimal one, so somehow you know what does minimal mean?
Okay, minimal in this case just means minimal, and so even minimal is not guaranteed to be unique, of course, but it just means a minimal set of equivalences where minimality is quantified in terms of just cardinality of the set.
I'm confused here.
Right. So it's like if you had a four levels of composition, there might be a couple different ways you could set up the associativity equations. Right.
Right.
And
if I say something like this, we get something that's a bit more complicated, but it will still return me the minimal set of associativity equations. And again,
was labeled graph the one that doesn't show all the additional edges?
Sorry?
The property labeled graph, does that?
There should be a property labeled graph. There isn't right now, but the one that doesn't show all the additional edges would just be you get out the underlying quiver and you say full labeled graph of that.
Can you even say like transitive reduction of the full labeled graph? Does that do anything useful?
So in a case like this, it obviously would, and it would give you, if you did transitive reduction of, it would.
Oh, brilliant. Okay.
Okay, so let me understand this. So you're labeling that thing at the top with these unassociated h.g.f type things, and then you're saying, go ahead.
When you say unassociated,
well, I mean that you've still got parentheses in it.
Yes, but the parentheses are the sort of canonical parentheses, right?
Okay.
So this arrow here, h compose g compose f. This equation is telling us that that's the same as h compose g compose f. We're just returning the right-hand side one because that's the canonical element.
But why do you? I mean, isn't it the axioms of category theory say that could just be written h.g.f without parentheses?
Sure.
Is that true? Yeah.
Sure.
Well, I think the composition here is a binary operator. I mean,
so maybe the rendering shouldn't show the parentheses unless necessary.
Well, okay. So
that is what's happening. This is like a precedence issue of circle dot, right?
Right. And maintaining it as a binary operator is incredibly useful later on when we do kind of theorem proving stuff over these things.
Okay, all right, okay, fine.
So this is just a way of saying we've canonicalized a bunch of, there are many, many different ways that we could have parenthesized these things, and the things on the right are the canonical ones that we show.
It's sort of unfortunate that we can't. It probably breaks lots of things if we use the actual function composition instead of circle dot or something like that. But
I did consider inactive of composition, but it just seemed too weird.
Yeah.
I'm sure we can have something which is a special character there that can have appropriate, behavior. Anyway, let's keep going. We could imagine an inactive composition that is actually introduced as a syntactic form. I mean, when would you want it to activate? But if that was okay.
Well, I mean, if there's an actual representation of this category, right? If you give an interpretation that says, these objects are actually, these data structures and these morphisms are these functions, then you might want it to evaluate.
Yeah,
but like the process of replacing the FGs and H's with the actual functions is sort of involved enough that you might as well also replace the composition part. You know what I mean?
Yeah, probably. I mean, these are symbolic FG and H for now. Okay, keep going. All right. So, boy, sure. This gets to be a surprisingly complicated diagram, surprisingly quickly.
Despite the fact that note that graph is totally trivial. If you look at the transitive reduction, this is just a path graph, but with all it's just the transitive closure of a path graph.
Yes.
Right.
Yeah, right.
Right, exactly. Well, actually, in that spirit, maybe I can show the sort of commutative diagram stuff. So obviously, one of the most fundamental things you can do in category theory and homological algebra is say, such and such a diagram commutes. So let me give you the simplest or a simple example of that, and then show how you can make it a bit more complicated. So here we have show actually both the full labeled graph and the reduced labeled graph. The underlying quiver structure has something like this. So here we have just a square, right? So you can see there are two different paths that take me from X to W. So what it means if I say I want this diagram to commute is that I want the function obtained by composing by applying F then H to be the same as the function obtained by applying G then I. And we can see that that's not true a priori from the fact that there are two edges that go from X to W in the full labeled graph. And hence, commutative diagram shows as false. So if I say commutative diagram Q, it will say false. But what I can do, I can see that just by looking at it, that if I want to make this diagram commute, I just have to impose an additional equivalence that H compose F is equal to I compose G. So if I
hold on. To get to that quiver full labeled graph, that is the transitive reduction of the graphs above. Is that correct? I mean, if I took line...
yes, yeah. So if I say transitive reduction graph of that.
Okay. So
it's also just what he put in. I mean, the input to create the category was just the quiver, and it only expanded out into this form.
Right. So
Right, but this is now showing explicitly that you've got different functions, different morphisms, H compose F, I compose G. And
sorry.
Go on.
Does commutativity of a diagram just mean that you have arrow equivalences for every pair of arrows from the same objects?
Not necessarily pair. It's in general just saying that every path for any two objects
in the top graph, then
right, every pair of paths between those two objects must be the same.
So if you had a third edge, you'd want all three of them to be equivalent.
Right, exactly.
Okay. And so for object equivalences in a category, are those isomorphisms or
okay. Isomorphisms are kind of their own thing. Isomorphisms are morphisms that are left and right invertible.
So you're saying that your notion of equivalence doesn't require that?
No, equivalence is much stronger than that. Equivalence is saying these things really are identical.
I see.
Isomorphism is a weaker constraint, which will again I'll show. I mean, there's a lot of built-in functionality for handling things like isomorphisms. I can show how.
Okay. Keep going.
Right. So if I say commutativity equations, it will return again the minimal set of equations necessary to force this diagram to commute. So if I add that in, now we get commutative diagram showing true, and reduced labeled graph now collapses this, this pair of multi-edges to just a single edge.
And if you do transitive reduction of that,
it won't change. Right, the underlying quiver structure is the same.
But wait a minute, you just added G compose I is the same as F compose H. Is that right? That was your
right, and so it managed to remove H compose F as sort of a redundant edge, and now, but both of those are both like they're transitive edges, so they're removed in the reduction.
Right. So the quiver doesn't care, right? Nothing that we're doing here modifies the underlying quiver structure.
Okay.
So this seems a bit trivial, but obviously, like, commutative diagrams get pretty complicated pretty quickly. So if I give a slightly more complex example,
right, I was going to ask. I mean, how often is that? I mean, in this case, it's pretty clear. Oh, there are these two. There's just these two edges you got to make equivalent. But in a more complicated thing, are there actually like lots of choices that you could go with?
Yes, yeah, no, exactly. So the actual set of equations that's implied by a commutative diagram is in general not obvious. There'll be many potential choices. And again,
you could do a grid quiver. That would be interesting.
Right, exactly. I mean, so this is the beginning of a grid. Oh, no, hang on, wait, this is meant to be the beginning of a grid quiver, but I've done something incorrectly.
F2 is repeated.
Oh, thank you. I mean to say, what do I want to say? I want to say G1 is there. Yeah, thanks, Jose. Right. This is the beginning of a grid quiver. So this is two, whereas this is just what one might call a commutative square. This is what in homological algebra would be called a commutative oblong. So it's just two commutative squares glued on top of each other.
All right, just to humor me, sorry.
Yeah.
Could you type abstract category of grid graph of something or other?
Yeah, do you have a favorite grid graph?
Oh, I don't know, grid graph 5.5.
Is it?
Oh, separate braces 5.5.
That? Okay, so this is. I'm not convinced that's going to term. I'm not. That's probably already too many paths.
Okay,
you might also want to say directed edges arrow.
Yeah,
true.
directed edges to true.
Right. Okay. If I say abstract category of that, I'm not convinced this is going to run. Oh gosh. Okay, we've got 53 morphisms there.
I mean, for graphs, 53 is nothing, right? I mean, that's
no, but like for categories, that's pretty hard to understand.
Is that 53 including all the transitive closure edges?
Yes. Yeah. Of course. Yeah.
Okay, so if you do transitive reduction on that, you should get a grid.
Right. Or if we say quiver graph.
Where are the F's coming from?
Well, because we didn't call the edges anything. So by default, abstract quiver and by extension abstract category calls the morphisms F1, F2, F3, etc.
That should probably be something a little bit more elaborate. I mean, it probably should be some more, not just a letter F. It should be some chosen, non-typable, formal thing of some kind.
Or shouldn't it be the dotted F or something? Isn't that what we do in other places?
Perhaps. Yeah,
Why not
perhaps.
just numbers?
Because otherwise you're not distinguishing. In this case, the objects are given numbers, but the edges are, I mean,
If you do canonical graph on a graph, does it convert everything to integers?
yes.
And actually, if it's an F, should it be indexed of F or subscript of F? Is indexed only for things that are really vectors?
I'm not sure.
Yes, it's you know, if you substitute an array there, it will use part.
But I mean, if we have 10 Fs, you know, that aren't, it's not, there's no vector involved. F is not a vector, but we just need 10 names. Would it be a mistake to use indexed?
I think yes, because I think we're going to have more support for things that are, you know, hidden crypto vector variables and things like that.
I'm not sure, Christopher.
Okay, let's move on because I think Jonathan probably has a lot to show. I just wanted to see something, a programmatically generated category diagram, because I don't think those are very common.
And I should say, like, you know, something like this. It's very, very non-obvious what the minimal set of equations you'd need to make this diagram commute would be. But I believe if I say commutativity equations, it will return what equations need to be satisfied.
And what is that algebraically? Can you just describe what was done to find those equations?
Well, actually, so what's really being done is graph theoretic, right? So to get a set of equations, you just need to pair off, you know, pairs of multi-edges.
I see.
And then we do essentially algebraic reduction on the, you know, on that set of equations to remove redundancies, and we just return the first.
Cool. Okay. All right.
And so yeah, so I was going to show. I mean, that lets me show that example now. But if I what I was going to show was like the case of a commutative oblong. What am I doing? Commutativity equations. For the case of a commutative oblong, that's now saying commutative diagram true. And that's the reduced labels graph with these multi-edges modded out, effectively. So anyway, so this immediately automates a lot of kind of proof methods in homological algebra and in category theory, because there's an awful lot of arguments in both fields essentially reduced to diagram chasing, you know, reduced to something where you generate some big complicated looking diagram and then you say this commutes, and so abstract category will tell you the minimal set of assumptions you need for that statement to be true.
Nice.
Okay. And I should mention, like, you know, once you introduce those equations, you can say what are the reduced commutativity equations and things like that. So you can say what are the commutativity equations if I mod out by the equivalences. And of course, in this case, because we've now got a commutative diagram, this thing has reduced to the empty list, even though commutativity equations is still that. Okay, so maybe I should show some computations you can do to kind of get interesting properties of categories out. So if I say, let's take the example of monomorphisms and epimorphisms, because they're a nice sort of simple starting place. So let me generate something like this. G2ZX. So I'm going to load those both up because we'll need them both. So a monomorphism is essentially a generalization of the idea of an injective function. So it's a morphism that is left cancellative or injective. So in that case, what it means is that, so we've got here we've got a morphism F, and we have two other morphisms that go into F, G1 and G2, from some common object Z. And so if I now say,
but don't you need to say that? It's not by name, right? You need to say it. No?
I need to say what? Sorry.
Which ones are mono and which ones are?
Well, no, so it will compute this, right? So you can see, by initially everything's a mono, but if I now say, circle dot, what do I want to say? I want to say circle dot f comma g1 equals circle dot f g2. So now the reduced label graph looks like this. So you can see we've got f composed g1 is equal to f composed g2. And if f is a monomorphism, that should imply that g1 equals g2. But it doesn't so far. We've still got g1 and g2 being separate. So you can see that f has now gone to false. F is no longer a monomorphism. But if we introduce the additional relation that g1 equals g2, then our reduced label graph collapses to this, and now f becomes a mono again. And so, as I say, this is effectively the generalization of what it means to be an injective function, because you're saying if I take f and I apply it, I want it to be the case that if f applied to g1 is equal to f applied to g2, then g1 equals g2. That's the definition of a monomorphism.
Okay.
And I could do the same thing with epimorphism. So I could say category 4 is that, and then so I want to say y, z, y, z. And we can say, sorry, category 4.
By the way, when it says monomorphisms, when it said something like f goes to false in the monomorphisms list or association, it's not, f isn't necessarily not a monomorphism. It's just that assuming that you don't know whether G1 and G2 are equivalent. And so you don't know whether it's a monomorphism.
Yeah, this is the question of generic.
People assume they're not equivalent by default.
Right, exactly. So you see that with commutative diagram and all this other stuff, if there is no explicit equivalence implied between the two morphisms, they are assumed to be inequivalent.
I see. Okay.
Which is like what we do with generic solutions to equations. It's solve versus reduce. There could alternatively be a reduce that would give the implied conditions necessary for f to be a monomorphism.
Right. And so, in fact, we do that again in the groupoid subsystem. We have functions for doing that will tell you what's the minimal set of equations you need to make things isomorphisms or monomorphisms or whatever. So actually, okay, let me show you. Right. So then epimorphisms would be, if I wanted to say circle dots.
The function properties, function injective, function surjective, and so on, does that too for normal functions.
Does what? Sorry. It
gives you the conditions for it to be true.
Right. Which is, by the way, very analogous to this monomorphism thing. So that's something.
It's not analogous. It's a special case.
Yes, I realize that, but I'm saying that the design thing, where what we have injective function of f is our way of determining whether that function. This is a more symbolic version of that notion of the function f. In the case of injective function of f, it's injective function of, sine of cosine of tangent of x or something.
It takes the body of a function instead of a
pure itself. Symbolic name. Yeah,
exactly.
By the way, maybe as a design question, maybe instead of calling it epimorphisms, it could be called like epimorphism Q, which means that you could both have like a second argument where you give it a. So first of all, if you say epimorphisms, it sounds like it should return a list of the things which are epimorphisms as opposed to like whether they are. And the other thing is that it might be nice to have like a 2-argument version of that where you give it an arrow and it tells you whether it's an epimorphism.
Right. No, I agree. So actually, this is one of the certainly related to one of the questions that I wanted to ask on the agenda, which was, so right now, these are just properties of abstract category. But I can also see an argument, and Stephen, I think we discussed this sort of back in December or something, that all of these things like monomorphisms, epimorphisms, etc., should be separate functions, in which case they could have properties that would do exactly what you're saying, Christopher, where you could say, you could feed it a second argument that takes in a particular morphism, or it could feed back an operator form that tells you whether a given arrow is an epimorphism or whatever. And I don't know what the best design for that is.
The corresponding terms for injective and surjective would be epimorphic and
right. So you'd want monomorphic Q and epimorphic Q.
Well, just monomorphic, and then it gives conditions.
Yeah.
Right.
Okay, but the thing that I think is going to determine a bunch of these design issues is what the interface between the abstract category way of setting things up and kind of landing, so to speak, in, you know, something where there are explicit forms for F and the objects and so on. Do we expect that there is such an interface, or do we think it's going to all live in the clouds?
Well, there definitely is, right? So the reason I'm calling all these things abstract categories is because, so in category theory, there's a distinction made between an abstract category, which is just something that satisfies the axioms of category theory, and a concrete category, which is a category that's equipped with a faithful functor onto the category set. So where in effect you are giving an interpretation of each object as a set, and you're giving an interpretation of each arrow as a set valued function. So for us, that would mean we'd want a notion of concrete category that, for instance, takes every object to a list and every arrow as a function from list to list.
Okay. And what would be some early, I mean, in terms of the rest of the system, how would that interface? What would like a commutative diagram chasing, you know, story be in terms of the rest of the system? Is that effectively giving us a bunch of equivalences between functions somehow? I mean, in other words, right. How would that, well.
Right, exactly. It would give you equations on functions and on function application.
Which is something we don't right now have. I mean, we don't have the capability to take lambdas effectively and do operations on those. And is this perhaps?
I mean, we do in the theorem prover, right?
In what sense?
In the sense that the operators you can think of as being abstract functions. And we're reasoning over equivalences between those operators.
Yes, that's true. That's true. All right, but keep going. This is
right. No, okay, whatever. So I was just going to show, you know, epimorphisms, bimorphisms, which are just, you know, things that are both monomorphisms and epimorphisms, things like that. We also have support for what else could I reason? I mean, what else is useful for me to show? Oh, okay. Like, just because I think it's instructive to other stuff. Clearly, notions like monomorphisms and epimorphisms are dual to each other in the sense that if I just took this picture and I inverted all the arrows and I reversed the direction of composition, I would get the corresponding epimorphism picture. And again,
so can I just say reverse graph? Will it do that?
You couldn't just say reverse graph because that wouldn't modify function composition in the right way, right?
Okay.
It would structurally give you the right thing, but what you actually want to do is say dual category, and it will give you the dual, which structurally is the reverse graph of that, but you can see the edges have been relabeled so that the
why those edges are not Bezier curves, I don't have the slightest idea. Why did they have little glitchifiers in them? That's so weird. See that? I mean, there's a bunch of straight edges there in the G1 compose F edge. Very odd. Okay, not this group, not this meeting. Okay, keep going.
Right, but anyway, the point we'll see that a lot where you've got two concepts that are you know, in duality, and that can easily be seen just by using dual category. Okay, so there's there are corresponding notions like retractions and sections. So if I take go back to saying
sorry, before you get to that, what's the difference between a bimorphism and an isomorphism?
Oh, okay, so right, so monomorphism, remember, monomorphisms and epimorphisms are just cancellative. So a monomorphism is left cancellative and an epimorphism is right cancellative. There's also the notion of retractions versus sections, which means left invertible and right invertible. So an isomorphism is one that's left invertible and right invertible, whereas a bimorphism is one that's left cancellative and right cancellative.
I see.
So the being a left inverse implies that you are right cancellative, and being a right inverse implies that you are left cancellative. So they are related, but they're not the same concept.
And this is what you were about to show.
That's what I was about to show. Yeah. Right. So a retraction is the left inverse of a morphism, and a section is a right inverse. So if I take, say, this, it's probably the simplest example I can show. I say retractions. An isomorphism is one is any morphism that's both a retraction and a section. In other words, it's both a left inverse and a right. It has both a left inverse and a right inverse. So you can see now that if I say, okay, right, because I've got an F and a G and they effectively, one goes from X to Y and one goes from Y to X, you can see there are two ways for me to get from X to itself. I can take the identity arrow, or I could do G compose F. And similarly, I could take the identity arrow on Y, or I could do F compose G. And again, a priori, we don't know that these two arrows are the same, but I could impose a condition that says G compose F is over tilde X. So I get that. And now you can see that G has become a retraction and F has become a section, because a retraction is a left inverse and a section is a right inverse. And although neither of them is an isomorphism. And similarly, I could say circle dot F compose G over tilde Y. And I get that. And now you can see that F has now become a retraction and G has become a section, and both of them are now isomorphisms. And so, sorry, was that? Okay, so what I can then show is we can look at a particular kind of category, which is a groupoid, which is a category in which every morphism is an isomorphism. So if I remove these again, I get back to that. If I say groupoid Q, it will say no, but I can say groupoid equations, and it will return the minimal set of equations I need to force this category to be a groupoid, which in that case is exactly the set of equations we imposed above. G compose F is X tilde, and F compose G is Y tilde. So if I include those again, that reduces, and now groupoid Q returns true. But just as with the commutative diagram case, it very quickly just becomes rather complicated. So if I say F1 goes from X to Y, G1 goes from Y to Z, F2 goes from, F2 goes from Y to X, G2 goes from Z to Y. And this becomes already really very messy. There are a whole bunch of different ways that I can get from certain objects to certain other objects and from certain objects to themselves. But I can again say, and again, it's like pretty obvious this is not a groupoid, because there are many different self loops for each object.
Right.
But I can say groupoid equations. Impose these. Now reduced labeled graph collapses to this, which is much more civilized, and groupoid Q returns true eventually. There we go. And so
hold on. Let me just understand this object.
So just remind me, what's a groupoid again? It's not a semi-group, would it?
No. So a groupoid is defined as exactly this, right? It's defined as a category in which every morphism is an isomorphism.
Oh,
but it's also defined purely algebraic, right? What's the algebraic definition of in universal algebra? What is a groupoid?
There is no universal algebraic definition of a groupoid that's inequivalent to the category theory definition. I mean, you could write a.
The joke is that a group is a groupoid with one object.
It's yeah. In effect, that's the definition, right? Because if you imagine a groupoid with one object, then every morphism is an isomorphism. So every morphism is invertible. You have identity maps by the axioms of a category, and you have associativity by the axioms of a category. So you've got a group where the group elements are exactly the morphisms of that single, category with a single object. So if you wanted to define it universal algebraically, you could just say, I replace the binary operation of a group with a partial function, and then I get a groupoid. But that's just a more elaborate way of stating the category theory definition.
And say the category theory definition again.
A category in which every morphism is an isomorphism, or every morphism is invertible.
And graph theoretically, isn't it also just that every connected component is the complete graph?
Depends on exactly how you define complete graph in this case.
Well, I mean, I guess it's transitive, and so and then everything is an isomorphism. So you have a sort of a undirected, or you have sort of the bidirectional arrows and for everything, right?
Right, but crucially, you can't have more than one pair of bidirectional arrows, right? It has to be commutative.
Sure, right, which makes it so you can't even have like I guess you couldn't even have like a multi-complete graph, if you know what I mean.
Right, exactly.
But so wait a minute. So a groupoid of size 4 with 4 objects in it. Can you show that?
I mean, again, you could see even with 3 objects, this got quite a bit. I mean, so first of all, which groupoid of size 4 do you want?
How many are there?
Well, there's one for every undirected graph with 4 vertices, right?
Okay, so how do you go from okay. This would be a triangle graph. Is that true? That this came from? Or a triangle with self-loops? Or it didn't necessarily have the self-loops?
The triangle graph would uniquely... So in effect, you want the graph to be undirected, right? Because it needs to be the case that for every... If you can go from X to Y, you can go from Y to X.
Sure.
So so this would just be the undirected graph, an undirected triangle graph that would define this groupoid.
Okay, I understand. But if you have a bigger graph, what, given a graph, how do you get the corresponding groupoid? Given an undirected graph, is the corresponding groupoid just the thing with every undirected edge turned into a pair of edges and, self-loops?
Except for self-loops, yeah.
Yeah.
Right,
So it's just
except plus all the groupoid equations.
What does that mean? You mean, can you show an example? Just the 4. Okay.
But this is an example, right? That's kind of the point of what I was trying to show. So, I mean, if you want to, there's no particular reason to do it this way around, but
do it for 4. Do it for 4.
Well, that's already. I mean, if that example, but what? I need a graph, right?
Okay. Well, so okay, you're showing me from this graph.
Yeah, I mean, I'm just for some reason you seem to want to do it with a. I'm going to just repeat exactly what I did up here, but with a graph. So if I say that. Category 2.
What is it actually doing here? Why is it taking so long? What is it actually doing?
Well, it's computing the category from that underlying quiver, which is obviously going to be quite complicated. Actually,
isn't it just going to be basically that?
Maybe I should start with that because that's more analogous.
You're not computing the groupoid directly. You're first computing the category.
There's nothing to say that it is a groupoid, right? So I mean, this is the category.
Well, yeah, you're not going straight from this quiver to a minimal groupoid.
No, I mean, we could have a function abstract groupoid which did that, but again, that's something I wanted to discuss here.
So out of curiosity, that computation time that was just for display, right? If you put a semicolon after, it would have been instant.
Oh yeah, no, of course, yeah.
Okay, yeah.
That's entirely display. So that's the graph we started from. This is the category from that. You can see these are going to get complicated really quickly because now you've got a bunch of cycles, and each one of those, every path through those cycles corresponds to a different new arrow you're going to introduce, and you recursively repeat that process, right? So this is why these things get so complicated.
So I'm sorry, just sort of zooming out for a second here. One of the things I've long been curious about is how do you put functions onto a graph? That is, how do you think of a graph? You could think of F composed with G composed with H or something as just a chain. And is this, in some sense, this is a way of decorating a graph with functions on the edges? Is that a way that I should think about categories in general? That it's a way of taking a graph and labeling,
it's a quiver with the axioms of function composition as usually defined. I mean, that's a way you can think about what a category is.
Right. Okay. So, because that's interesting as a general thing in language, because it's basically saying, just as we can define, we have tree-like expressions usually, but these are in a sense graph-like expressions. Is that a fair statement, or is that, normally we have functions that are sort of composed with each other in tree-like forms, but this is.
But there are many graphs can be models for many different phenomena. So even for function composition, like a neural net, those are function compositions, but we describe how they compose.
What is the relationship between a neural net and a category way of saying how things compose?
Because you have a bunch of outputs that are going to connect to a bunch of inputs. Like what's the topology there? How are things wired up?
Yes.
And you think of a circuit, combinational circuit. Those are the blocks are functions. The wires are compositions.
As opposed to in this case where the wires are functions.
Right. There are many, many ways that graphs are models, structural models for things in life, including for functions.
Okay. I have more to ask about that, but keep going.
Okay, well, I mean, there's a bunch of functionality. Okay, abstract category has loads of functionality for doing similar things, and let me not, in the interest of saving time, let me not go through all of them. But like, for instance, you can compute endomorphisms, automorphisms, initial objects, terminal objects, constant morphisms, co-constant morphisms, zero objects, all those kinds of things.
So when you say you can compute, for a given category, go ahead.
Does that largely reduce to graph algorithms?
Yes.
Cool.
Yeah. So most of what we're doing here is doing essentially abstract algebraic computations via graph theory.
Which means it should scale pretty good.
Mm-hmm.
But so, for example,
is this a framework for finite categories only, or do you envision this for?
Right. Okay, that's a really good question. So, so right now it only works for finite, for things you can specify with associations. So for finite categories, of course, most categories that category theorists would care about are not just infinite; they're actually non-small. So again, like in CT, it's common to make a distinction between small categories and non-small categories. So a small category is one where the object set and the Hom set, the set of morphisms, are both sets. But in most categories, they won't be sets, they'll be proper classes. So for instance, in set, they clearly aren't sets because the object set is the class of, is all possible sets, which, can't be a set, it has to be a proper class. And similarly, for similar reasons, top, the category of topological spaces, or rung, the category of rings, etc. These are all non-small categories. So what would be lovely is if we had a purely symbolic way of representing infinite and indeed non-small categories.
That's what we did in the pure math entity store packlets, was basically just symbolic representations that couldn't do any computations with them.
Right.
And how, and Ian, if you fed in this category theory capabilities into those symbolic representations, could you actually get more mileage there?
It's kind of why I was asking Jonathan. I don't even see how they fit together, because this is so, this is like discrete. You have finite numbers of objects and edges. You're not trying to reason about, infinite things.
Well, the question is there some quantified version of this?
When you say infinite, I mean the sets can be infinite, right? There's no.
Well, so it would be like you would have an infinite number of vertices in the graph.
Right. Okay.
Or
that's
potentially
what I thought you meant. But
not even a
themselves.
set of vertices. It might be a class of vertices, like Jonathan was saying.
Sure. I got it. Yeah.
Okay, but so when you say you can test for automorphism, that what you're saying is you can give the conditions on one of these categories for the thing to be an automorphism. Is that right?
For a given morphism to be an automorphism, yeah. So I don't know. Let's do a boring category. And just as I was showing before, with monomorphisms, epimorphisms, isomorphisms, etc., we can do automorphisms. We can do endomorphisms, etc. So in this context, an endomorphism is any morphism that maps an object to itself. An automorphism is any endomorphism that is also an isomorphism, etc. So there's a whole sort of zoology of these things.
Okay.
Right. Anyway, all I wanted to say was that abstract category is, I've tried to design it so that it does kind of all the standard bureaucracy you would expect from a cat. Every special kind of morphism, every special kind of object, etc. should be, there should be a way of computing it. Okay, but that's probably I've probably said enough about abstract categories for this.
Can you compute the inverse morphism? Like for your groupoid, can you ask for inverse of any morphism.
Yes, I mean, in effect, that's what so the full version of retractions and sections would do that, right? That if we were to break that out into if we were to break those out into separate functions, it would tell you what a given morphism, it would tell you not just this morphism is a retraction, but what morphism it is a retraction of, and same with sections.
Why there's no way, like the reduced graph doesn't contain the inverse, right? There's no inverse in the reduced graph there for the groupoid.
Wait, what do you mean?
Well, like you say that groupoid is the category that contains all of the inverses, right, for every morphism.
Right.
So does it mean that the F1 should have an inverse?
Right, which is F2.
Then, okay. How does it compute that it's F2 is inverse?
What do you mean?
Or can you actually compute it? Is there a way to compute this? Like ask for it, like give me inverse of F1 so that it give me F2.
That's what I'm saying, right? So in the full version of this, you would want to say what is a retraction of what and what is a section of what, and therefore.
Right. So you might want to have a function, a property there called inverses or something, which would give you for every object, for every morphism, it would give you the inverse morphism, just as pairs.
But it's not right. But the point I'm trying to make is that it's not going to be as simple as that, right? Because a single morphism could have multiple retractions. A single morphism could have multiple sections. So it's going to be a list of stuff in general.
I see. So there isn't a unique inverse of a morphism. Is that what you're saying?
I mean, I don't see why. I mean, obviously there are categories in which there would be, but in general there wouldn't.
Okay, in general there isn't. Okay, I didn't know that. I mean, yeah.
Well, in general, there's no inverse.
There might be no inverse, but can there be two inverses?
Yeah. As I say, a given morphism can have multiple retractions, for instance. That happens a lot in topology.
Okay. Then the diagram can explicitly show that F2 is a F1 inverse, if it knows that. Right?
I think that diagram is showing that. I mean, it
is. Look, because you can see there's only one arrow from X to X, and it's X tilde.
But if F2 and F3 were both inverses of F1, what you would see there is an F1 arrow going one way from X to Y, and the F2 and F3 arrows both going from Y to X. Is that correct?
I mean, yeah, this is why I showed the earlier example, right? That's why I tried to take pains to illustrate the simpler case, something like this, right? So in this case, you can see that F and G are not mutual inverses because there are multi-edges here. G compose F is not the same as X tilde, and F compose G is not the same as Y tilde.
Okay.
So you still have to trace it in order to see it. I'm just suggesting maybe you should actually, as a label, show that G there, G1 is F inverse.
Right, which as I say, would be exactly what a full function form of sections and retractions would do.
But on the diagram, just not asking for any properties, just by looking at the diagram, I should already understand what is the inverse of a morphism. Not like tracing it over any loops there.
So Nick, what are you actually suggesting is drawn on this diagram?
Not on this one, when the groupoid, just the labels. When you have F1 and G1, F2.
Obviously, I agree. If we had a function, this is related to what we were discussing earlier, right? If we had a function which represented abstract groupoids, then I absolutely agree it would make sense to show the inverses. I don't think it makes sense to show the inverses on an abstract category, because then why wouldn't why wouldn't we also label the retractions or the sections or the whatever?
Right. So it just seems like abstract groupoid is something that there's
another option for groupoids would be to just use a single edge that's labeled with both forms. I don't know if that would mess with anything.
Yeah, I mean, you again, like for groupoids in particular, you could imagine having special rendering where instead of these being directed edges, they're undirected, and they're as you say, they're labeled with mutual inverses or something. You could, yeah, that would make sense for abstract groupoid. It wouldn't make sense for abstract category, I'd argue.
Right. Sounds right to me. Okay, onward.
Right. Sorry. Anyway, what I want to get onto is actual not just bureaucracy, but actual computation. So maybe I should show something like abstract functor. So if I take, again, let's just generate a boring category, x, y, y, z, something. And I say abstract functor category. Let's call that functor. Obviously, a definition of a functor is just it's a function between categories that preserves function composition, that preserves composition and preserves identity. So, functor applied to f compose g should be functor of f compose functor of g, etc. And all the axioms should be maintained. So it's effectively a homomorphism between categories. So if I show the input form of functor, you can see what it's doing is it's taking in an underlying category. Let me break this out here. It's taking an underlying category. It's saying, here's an association of object mappings telling you what maps to what. Here's an association of arrow mappings telling you what maps to what. Here's a list of new objects and a list of new arrows that are produced. And here are additional equivalences between objects and morphisms that are produced in the image. We also want to be able to specify whether whether this functor is covariant, in other words, whether it preserves or reverses the direction of arrows and compositions, and also what the new symbols for composition and identity would be in this new category. That's the sort of full form of a functor. So you see in the default case, when you just feed it a category, it will assume an endo functor. So if I say endo functor q, it will return true. That just means a category, a functor from a category to itself. So if I say full labeled graph, we can see.
But you could give abstract functor of category 1 comma category 2, and then it would be a mapping, or category 1 arrow category 2.
No, you couldn't do that because there would not be enough information in just that mapping to tell you which morphisms map to which other morphisms. Okay. You have to essentially build it up algebraically like this. So what I was going to show.
What does abstract functor of a category, like what is it doing?
It's showing this endo functor.
Right, so it's treating the trivial case where you've just got an identity functor from the, or again, what is called an endo functor that just maps a category to itself.
Okay.
So if I were to then say, so I could do something a bit more interesting. I could say, so here I'm going to have an association of object mappings. So I could say X goes to A, Y goes to B, Z goes to C or something. And then I could also say, I don't know, I could have a mapping between arrows. I could say, F goes to func. So that's no longer an endo functor. These two categories are no longer equivalent. Actually, maybe it's easiest if I show domain and image. So you can see this is the category that it's now being mapped to with the objects and the functions relabel. And obviously func is now used in the, not just in the original arrow, but in all the compositions that involve that arrow and so on. But I could also say something like, I could also introduce some new objects. I can introduce U and V. So if I say, so now domain is the same, but image now looks like this. I could introduce some new arrows. I could say, F2 goes from U to V, and I get, now my image looks like that. Or I could say,
wait. That fourth argument, UV, what the heck is that?
So this is these are the new objects that are introduced by this functor. So a functor can introduce objects and it can also remove them. So it can introduce, and it can introduce arrows and it can remove arrows. So so you have to specify which new object and which new arrow is being introduced, which is what these two arguments show. And then you can also add equivalences that effectively take objects and morphisms away, just like they do in ordinary categories.
Okay, so what's argument number 2?
This is these are the mappings between objects.
Okay, and the argument number 3 is the mapping between morphisms. And argument number
arrows could be, because again, like you're actually mapping between arrows in the underlying quiver because these names should be preserved when you do compositions. Sorry, just to
Is it because it's sort of convenient to the automation of having sort of category to category, and then you just add to it, basically?
Right. In effect, yeah. One doesn't want to have the situation where you're giving directly mappings between morphisms, because then you could have a situation where a person is specifying a functor that is actually ill-formed, where the image doesn't satisfy the axioms of category theory.
Right.
So if you specify the mappings between the arrows, then abstract functor can take care of that for you.
Right. Makes sense.
And again,
Can I ask, object, you said objects and arrows can be removed. They can only be removed through equivalence, right?
Right, exactly.
Whereas new things can just be added wholesale, and then you add additional.
Right, and that, again, that's part of the sort of axiomatic definition of a functor, that every object has to map, every object in the domain has to map to an object in the codomain. Every functor in the every morphism in the domain has to map to a morphism in the codomain. But there could then be non-trivial equivalences between those objects and those morphisms.
Yeah, I guess I could rephrase, like, you don't have like partial functors. Like,
I think there is a notion of partial functors, but that's not, abstract functor isn't intended to support that. And I think they only get used in rather abstruse parts of theoretical computer science.
How many arguments does abstract functor have?
Well, there are lots of different ways of specifying it, right? So, I mean, again, the true form is this association here. This multi-argument version is just a sort of a convenient way of specifying it.
Okay.
But that was also going to show, if I could impose something like B equals C, and then that would reduce to that. And so that's a way that I could get rid of objects. I could get rid of arrows in the same way. And if I wanted to, if I took, so this is a covariant functor, I could take this thing and I could say functor 2 equals that, and I could just swap, where is it?
Covariance.
Covariance true, I could change that to false, and now I get a contravariant functor, and if I show a full labeled graph of that, now you can see this is the same as full labeled graph of functor, but now, arrows have been reversed, function composition has been reversed. And so functor Q will now say false to covariant functor Q and true to contravariant functor Q. But there are other things that you could check. So for instance, one has a notion of full functors and faithful functors, for instance. So a full functor is one that's injective on Hom sets, and a faithful functor is one that's surjective on Hom sets. So if I take something like this, and let me figure out a minimal case of something like that. So if I get rid of these for the time being. Let's do an image of that. Okay, so if this introduced a new arrow between, say, B and C, so if I introduced G2 from B to C, okay, sorry, actually, before I do that, let me just show, if I call full functor Q, return true. If I call faithful functor Q, return true. And because both of these are true, it will also return true for fully faithful functor. If I now have this thing introduce a new arrow, so if I say G2 goes from Y to, or from B to C, I should say, sorry, like that. So now we have something that looks like this. Then full functor Q will now return false. Faithful functor Q will now return true, but faithful functor Q will now will still return true, because in effect what we've done is if we treat this functor as a collection of functions between Hom sets, i.e. a collection of functions between the sets of morphisms between pairs of objects, that this functor is now no longer injective for this particular case, because we're generating a new arrow between A and C. So because of that, it's no longer a full functor, although it is still a faithful functor because it's still surjective. Similarly, if I were to take this, if I was to have this be, I don't know, let's say something like, actually, let me make the category now have multi-edges in it. Maybe that's an easy way to show what I mean. Yeah. And so now if this took away, if I had something which now stripped out one of these morphisms like this, then full functor q would return true, but faithful functor q now returns false, because now, in effect, by imposing this equivalence, we've made this functor no longer surjective on the Hom sets. Anyway, so all I'm trying to say is that there are, just like for categories, there are lots of properties of functors that we could try to compute in this way. We could ask for, what's the complete list of, or what's the complete association of mappings between the morphisms, lots of these kinds of things.
Okay.
Does that all make sense? Okay. The reason I wanted to introduce functors, though, is because so many of the actual sort of interesting categorical constructions depend on, well, they depend on diagrams, which are in turn formalized in terms of functors. So in category theory, the way one thinks about a diagram is that it's just a functor from an index category, which is usually finite, onto another category, which is usually not finite. So it's a way of sort of parameterizing infinite classes of morphisms and objects by finite numbers of objects and morphisms. That's formally that's what a diagram is showing. And so a lot of category theoretic constructions like products, coproducts, push-outs, pullbacks, equalizers, limits, colimits, all these things are defined over diagrams and therefore require an a priori notion of functors. So maybe I can show a few of those just to give some interesting motivating examples. So let me show something like abstract product. So this will take a list of objects. So if I give X and Y.
I have a feeling the name abstract product is not going to be one that can make it, but that's a different, maybe, I don't know.
I'm open to other names.
Product category.
Product category is something else. A product category is a Cartesian product of categories. This would be more like categorical product, which is something different.
Okay.
Okay. But okay, so you can see, so this is the labeled graph version of that, but what is also interesting is the universal full labeled graph. And let me also show universal reduced labeled graph, and then I'll explain what's going on. Okay, so a categorical product is effectively a generalization of lots of different kinds of products, things like Cartesian products of sets, direct products of groups, Cartesian products of topological spaces, etc. So probably the easiest way to see what's going on is if we look at this universal reduced labeled graph. You can see we fed it two objects and which were X and Y, and we've got this new object X, which is X times Y, or the product of X and Y. And this is defined to be, in effect, the most general object that sort of that could be thought of as being a product of X and Y. And the way you can read that off from this diagram is let me think of a way to explain this. Okay, probably the easiest way to think about this is if you think about every object as being a set and every arrow as being a set inclusion map. So you can see, so now you can see this X times Y is just going to be the intersection of X and Y, because you're saying X times Y is a subset of X and X times Y is a subset of Y. And what this dashed line here is doing is it's indicating a universal property. It's saying any other, actually, let's show the full universal labeled graph. It's saying any other object, I've just realized X and Y was a bad choice of name. Y is I'm using Y to indicate the additional object. Let me do X1 and X2. I'll fix that in a later version. But okay, so what this is saying is that any other object Y, such that there exists an arrow F1 from Y to X1 and an arrow F2 from Y to X2, such that this diagram commutes, it will be the case that there is a unique morphism F, which is given by this dashed line from Y to X1 times X2. So it's telling us that not only is X1 times X2 a subset of X1 and a subset of X2, it's telling us that it is in effect the largest subset of X1 and X2, because if you had any other set Y that was a subset of X1 times X2, then that subset wouldn't, that was a subset of X1 and a subset of X2, it would in turn be a subset of X1 times X2. So this universal property is a way of saying it's the largest canonical set that is contained in both X1 and X2, if that makes sense. So it's in that regard that you can think of a categorical product as being effectively it's the general construction of which direct products, Cartesian products, topological products, etc., are all special cases. And
how does it relate to type products and type theory? Is it related in any way?
Yes, yeah, absolutely. So I mean, all of category theory is deeply related to type theory, right? Because in effect, if you think of every object as being a type and every function as being a function that's bool arrow bool or bool arrow int or whatever, then a category is just a specification of a type semantics. And then these are exactly product types.
Okay.
And so you know, if you were to think about this in like, I don't know, a typed imperative language or something, pi1 and pi2, these projection maps would be essentially getter functions that you would, you know, you've got a product x1, a product type x1, x2, and you've got a get that returns something of type x1. You've got another get that returns something of type x2.
Hey, Christopher, is all this stuff relevant for visualizing, you know, complicated compound types in the compiler?
I don't think so. I don't think there's the, like, I think that the types in the compiler are realistically not nearly this complicated.
Okay. Even when they're generated automatically?
Yeah.
Okay. All right. Okay.
Right, and you know, and so you could take products of, you know, arbitrarily many things. You get a more complicated looking universal property, which reduces in some nice way. Hang on, if I wanted to, I could get. Let me just. Hang on, if I show something like this, I could get the dual of something of a sort of product type construction. And that's something like this. So a code product.
Yeah, okay, go on.
Well, a code product, which is just the dual concept to a product, is now effectively, you know, again, essentially you can think of this as a generalization of a direct sum of modules or vector spaces, or a disjoint union of sets or topological spaces, or, you know, a free product of groups or something like that. So what this is saying now is, okay, let's go with the two object case. So this is now saying, so X1 sum, this is often called a categorical sum or coproduct. So it's saying X1 sum X, the sum of X1 and X2 is defined so that there's an inclusion map from X1 to that, and an inclusion map from X2 to that. And again, it satisfies a universal property. So in exactly the same way, if you think about this now in terms of sets and inclusions, you're saying X1 sum X2 is such that X1 is a subset of it and X2 is a subset of it, and it's somehow the smallest set such that X1 is a subset and X2 is a subset, because if there were any other set Y such that X1 were a subset of Y and X2 were a subset of Y, then X1 sum X2 would be a subset of Y. And so it's in that sense that we can say this is a sort of direct generalization of the disjoint union of sets, or of spaces, or direct sum of modules, or whatever. And again, it's sort of the power of this lies in this universal property here. And so, because you know, in effect, this is quantifying over all objects and morphisms. It's saying any object Y such that there exists an F1 from X1 to Y and an F2 from X2 to Y, there must exist a unique morphism F from X1 sum X2 to Y. And so because these are universally quantified things, we can embed something like this in a larger category. So I can say something like coproduct universal, what do I want to say, universal coproduct category, I think. I might have to double check yeah, it's that. So then this will return an abstract category object. If I had if I wanted to, I could embed this coproduct in some larger category that contained an object X1 and an object X2, and it would handle this kind of universal quantification over morphisms for me. But okay, so let me then talk about some general. The reason I'm introducing these concepts is both to show the power of these universal properties, which are sort of fairly fundamental in category theory, and also to build up intuition for abstract limit and abstract co-limit, which are very, very general class, effectively super functions that encompass a load of other stuff, because limits and co-limits are so fundamental. But they kind of don't make any sense unless you motivate them with a bunch of examples first.
Okay, hold on. Can we get a basic architecture here? So we've got these abstract categories, which are these finite category things, and we have a whole bunch of operations on them that are building up. I mean, these products are building up sort of products of objects and things, and maybe we'll have you know, there are various other kinds of constructions that build up bigger kinds of categories and so on. Is there some moment where we're going to be starting to do very non-trivial computations with these, or is it largely building up essentially the bureaucracy of categories? which is
So-
highly useful. But go ahead.
Well,
Yeah.
so most of this is building up the bureaucracy. But again, it depends what you mean by non-trivial computation. So something like doing effectively diagrammatic theorem proving, which is what we were doing before with commutative diagram. In effect, you could argue that is non-trivial computation.
Yeah, sure. I mean, people spend all kinds of, there are all kinds of exercises in books about, arrow chasing and things like this, diagram chasing.
Exactly. Yeah. And so it really depends what you mean. I mean, I would argue, for instance, that the functions like abstract limit are doing also very non-trivial computation.
Okay, well, that's yeah.
But again, like, I don't know. At some level, the distinction between what is bureaucracy and what is non-trivial is a bit blurred.
I understand. But so, in terms of kind of relating, for example, to physics project kinds of things, the big versions of this, where things aren't explicitly named, will end up being more like sort of physics project stories. Is that true?
Sure. And, for instance, okay, once you've got, the reason I focus so heavily on bureaucracy is that once you've got the bureaucracy down, everything else becomes quite easy. So, for instance, once you've got a good design for abstract functor, representing something like a, compact closed Dagger-symmetric monoidal category, which a multi-way system is, becomes really easy because the monoidal structure is just an abstract functor on a product category that satisfies certain coherence conditions. The dagger structure is just an involutive functor from a category onto its opposite category. The compact structure is just a pair of sort of distinguished morphisms, etc. So representing these kind of more sophisticated objects becomes really easy once you've got the bureaucracy.
Does that represent a general multi-way? Go ahead.
What you were saying for the different representations in the physics project, those are finite things, or
so
like these are finite categories?
Most of the time they would not be finite. So most multi-way systems don't, because most computations don't terminate. Most multi-way systems are not finite graphs.
But so in this framework, you don't have a generator of multi-way systems. You have a way of explicitly giving a multi-way system as writing it, not as a graph as we might normally write it, but as a category specification. Is that correct?
Right. Although, I mean, there's no reason in principle why you couldn't generate categories from rules. It's just that that's not currently supported. And, for instance, in the type theory and functional programming context, that's exactly what one does, right? One specifies a set of type constructors and one gets a category out.
Yes, although one expects to be using those by hand. One doesn't expect to have a generator thing that is just churning out, complicated types.
Well, in independent type theory, you can do that, right? You can have a higher inductive type that is exactly a generator of complicated types.
Right.
And, one of the things that came out of the sort of connection with homotopy type theory that Xerxes and I worked on is that, there is this nice correspondence between higher inductive types and multi-way systems that have differing levels of completion.
Okay, this is good. By having this explicit form of category theory, it will be easier for people like me to understand that.
Right. But in effect, all that's doing is it's saying that there is because of essentially Curry-Howard isomorphism reasons, there is a one-to-one correspondence between multi-way rules and type constructors. And the resulting multi-way systems that you get out are exactly, or are themselves in one-to-one correspondence with the symmetric monoidal categories you would have got from those type constructors.
Okay.
That's kind of
and then these various properties. So for a given multi-way system generated by a particular, let's say, string rewriting rule, you can start asking all these kinds of, all these different properties of categories. You could ask for those essentially multi-way graphs.
Right, exactly. Which in the language of monoidal category theory, the multi-way evolution graphs are really string diagrams. And so once you have symmetric monoidal categories, you could request out the string diagrams, and you would get essentially something that's trivially interconvertible with a multi-way system.
But nevertheless, these other properties of categories, you would also be able to ask about the multi-way system.
Right. So you could ask, for instance, is there an inverse, are there left and right inverses for a particular rule application or something? That would be, the analog of retractions and sections.
Cool. Okay. All right. So How far do we have to go to get to the symmetric monoidal category business? How many more layers of concepts do we have to have?
Unfortunately, quite a few. I mean, but it depends. So I wasn't focusing too much. I mean, there is a prototype of symmetric monoidal categories and things in here, but given that, as I say, that once you've got a notion of functors and you've got a notion of product categories, those things are kind of trivial. I've been focusing much more on the constructions of essentially more fundamental categorical constructs.
Fair enough.
So yeah, okay. So for instance, what I wanted to show was, okay, you could take these, you can take things like products and coproducts and you can generalize them a bit, and you can get things like pullbacks and pushouts. So if I take, let me say, abstract cospan. So a cospan is just a pair of morphisms that have a common codomain. So if I say something like that, F, G, that will give me a cospan. So then I could say, full labeled graph. Oh no, wait. Wait, what do I want to do? I want to say, hang on. What do I want? Oh no, what I want is pullback. Full labeled graph. There we go.
What the hell is that? What is a pullback?
Right. Okay. So in effect, a pullback you can think of as being a generalization of the concept of a categorical product. So again, if I show,
Don't you think of it as a substitution?
I don't know. Then I might understand it, but I don't see that yet.
I think it is basically a substitute. I mean, it's one where you replace the innermost thing, basically.
Jonathan?
Right. Okay. So yeah, no, that is a useful way to think about it. So okay. The concept originally comes from topology and homological algebra, and the concept of fiber product.
Or geometry, differential geometry.
Or from differential geometry, but yeah, one also has a concept of fiber products. But in a sense, in a purely structural or graph theoretic way, you can think about it as being just, hang on, if I say cospan category, no, wait. Sorry, I forget exactly what the syntax is.
You have properties? If you say cospan.
No, I haven't implemented properties for this yet, unfortunately. Oh, whatever. No, never mind. There is a way to extract the cospan category, but it doesn't really matter.
Okay, so what roughly is this?
Right. Okay. So here you've got a span, right? You've got a cospan. You've got an arrow from X to Z, and you've got an arrow from Y to Z. The cospan is sort of the minimal set of the way you can think about the pullback of that cospan is that it's the minimal set of objects and arrows you would need to add to make this into a commutative square. So you can see what we've done is we've added an object P and a pair of morphisms P1, P2 from P to P going from P1 going from P to X and P2 going from P to Y. And if I say, and this square is commutative because if I now ask for the reduced labeled graph, you can see that by default, F composed P1 and G composed P2 are equivalenced. And this thing is universal. So if I ask for its universal pullback or I ask for its universal reduced labeled graph.
What does universal mean?
Well, so again, it's this concept of universal properties that we already saw in products and coproducts. So what you're saying is, so this object P completes this commutative square, but moreover, it's the most general object that completes the commutative square because any other object Q such that there exists an arrow from an arrow Q1 from Q to X and an arrow Q2 from Q to Y, it is necessarily the case that there is a unique morphism U from Q to P that forces this diagram to commute.
By the way, from a design point of view, you are generating variables with sort of special names with wild abandon here.
Right. Okay, so that's a good point. So right now, in order to avoid, name clashes and things, a couple of points on that. One is that as we saw already with things like abstract functor and abstract category, where you've got symbols for identities and symbols for composition or whatever, like all of these things are modifiable. So if you wanted to change the name of the object that appears in the pullback, you could change it from P to whatever. The other thing to note is that right now, know you'll probably think this is a hack, but I don't know whether it's more or less of a hack than using formal symbols. But right now, the generated things are always strings to avoid.
You're a big string enthusiast. Untangling the strings to put it to kind of make the pun in multi-way system is going to be a huge undertaking here. But yes, right. I mean, look, we've got a whole class of these things. Like same thing with axiomatic theory. We've got all these things which are sort of formal objects that have to be generated. They have names. They're still used elsewhere. I think it remains a bit of a tangle what to do with all of this. And
is there a fundamental problem with just like unique and symbols and things?
Well, there is in terms of displaying it. It's ghastly.
Well, maybe we could have something like unique, but where it makes, let me think. I mean, in a similar way to how we have the dotted symbols. Well, I'm thinking if there's somehow we could have symbols that are like displayed in a nicer way, even if they have some crazy UUID like name.
Well, I think that's probably the right thing to do. Yes, I think that's probably the right thing to do.
Which by the way, I mean, right, I mean, we could have something like unique, maybe. I mean, yeah, I mean, we could have like a version of unique that puts things into some special context in which their names are, and the front end knows that if it's a symbol from this context to elide its name. Which, by the way, would solve another problem with unique right now, which is that unique creates things in global, which is a problem because if you have like internal code and you call unique, then you're creating a bunch of global symbols as opposed to symbols in some internal private context.
That's a good idea. Can we move that? Can somebody take a note of that and let's do that? Talk about that in the next ILD meeting. There's a special context for unique symbols,
Sure,
which should break nothing. It should break nothing to change that, even for the unique function. Unless somebody has depended on it in some crazy way. Okay, please, onward, Jonathan.
But doesn't your code clear global?
What?
Yeah. I'm sure your code just do clear global backtick star.
Why? What?
No, I'm kidding.
Okay. Okay. All right, a cospan. So we have some vague understanding of what a cospan is. But wait a minute, I still didn't get the intuition for what a pullback is.
Right. Oh, I mean, like cospans are easy, right? Cospans are just, pairs of things that have the same codomain. So a pullback, so you can see that in a sense, a pullback is just the same as a product, but we've got this additional, we've got an additional object. So you can see that in effect, P is just like, if you think about this in terms of sets and set inclusions again, we've got two sets X and Y that are themselves subsets of some additional set Z, and P is in effect the largest set that is such that P is a subset of X and P is a subset of Y.
Yeah, right. Yeah.
Why do we care? I mean, so what's the intuition? I mean, what somebody said substitution.
Two sets.
What's that?
That's the intersection of two sets.
Is a
Right.
pullback?
Well,
Okay.
So just as the product is a generalization of set intersection, for the reasons we stated before, a pullback is a generalization of a product.
Okay.
It encompasses it. So in the special case where either Z doesn't, if you got rid of F, G, and Z, or you just have Z be trivial, then you'd recover exactly a product. But in effect, you can think of this as being like a product with an additional gluing transformation. That's
Okay.
maybe the right intuition for it. And similarly, a push out of a span, which is the dual notion, is effectively like a disjoint union with a gluing operation. So it is itself a generalization of a categorical coproduct. So if I take abstract, if I say this is abstract span, and I say push out.
Is the correspondence of names to push out rewriting in graphs coincidental, or is there some connection?
No. I mean, what do you mean? They are push-outs. Categorical graph rewriting deals with single push-outs and double push-outs. So, in fact, I can show you that, right? So, I mean, this was the work done by Hartmut Ehrig and people like that back in sort of the 1980s. Was when this deep connection between compositionality and algebraic graph rewriting was sort of really studied.
What is algebraic graph rewriting?
Well, so graph, treating graph rewriting rules as abstract algebraic structures, which then allows you to use category theory on them. So in compositional and algebraic graph rewriting, your span. So every graph rewriting rule is a span where you have that goes from an interface graph K to the left-hand side of a rule, and the interface and an interface graph to the right-hand side of the rule.
Oh boy.
And then,
okay. Yep.
Right. So this would be called a graph production or a graph rewriting rule. So you can think. So the intuition for this is okay. Right. So the intuition for this is that L is L. All the objects here are graphs. We're working in the category of graphs. L is the left-hand side of the rule, R is the right-hand side of the rule, and K is the index graph, which you can think of as being the sort of invariant subgraph that's left over when you apply this rule. So then in DPO, which is kind of the most general form of graph rewriting that's currently known, what you're doing is you're exactly applying a push-out square and a push-out complement square of this span. The push-out square, the responsibility of the push-out square is it takes a graph G, and the intuition is it extracts out a subgraph that's isomorphic to L and leaves essentially dangling edges that are given by the index graph. And then the push-out complement square glues in to this index graph, to the invariant subgraph, a graph isomorphic to R. And so it's encoding these two steps. So the two push-out diagrams that are glued together are encoding these two steps that one does in the sort of general form of graph rewriting. And so, yeah, as you undoubtedly know, that the sort of the two standard versions are SPO, which is where everything is done with a single push out of a single span, and DPO, where you also have an injective morphism from G to L, and you do two push outs of that. So anyway, so
okay.
and so there would be a nice.
I prefer my description in terms of hairs and things. It's more mundane. But yes, this is lovely.
Well, the hairs are exactly. I mean,
I know.
K is a formalization of your concept of hairs.
Yes, right.
Anyway, so one nice thing is that if we do have a Wolfram language implementation of graph rewriting at some point, this would integrate quite nicely with that. That there should be some nice way of getting out, the span that corresponds to a given rule, the injective monomorphism that, or the monomorphism that corresponds to a given, to a given graph match, and the double push out that corresponds to a given event. That all of those things would be extractable, for instance, from a Wolfram model multi-way system.
Yes, or even a regular Wolfram model. Right, not even the multi-way case.
Sure. If I don't know, because the event specification for Wolfram model is not quite as rich as the event specification for multi-way systems. So I don't.
I understand that, right?
For it, but yeah, in principle, yes.
And that's a piece of unification that we still need to talk about graph rewriting in physics project versus graph theory versus chemistry, etc. Okay, but let's go back to category theory here.
Right. Okay. So what I'm doing is I'm trying to show a bunch of examples of limits and co-limits to kind of motivate why you need this generalization. So as just a last example of that, let me show things like equalizers and co-equalizers.
I'm sorry, where did you show a limit?
I haven't yet, right? Because the problem is if I just show a limit, it'll be utterly incomprehensible if you haven't seen one before.
Okay.
So this is why I'm showing lots of motivating cases. So an equalizer, if we start with two, let's say x to y, g from x to y. So if we start with a pair of morphisms between the same two objects, and I say also say universal. So the intuition behind an equalizer is that it's essentially a generalization of the set of solutions to an equation. So, well, in abstract algebra, it's exactly the sort of the difference kernel of two functions. So the idea here is you've got a pair of morphisms which you can think of as being like functions from x to y, and we've got this arrow eq and this object e that we're introducing, and we're saying that f compose that hang on, if I take the reduced version of this, you can see we're imposing that f compose is equal to g compose eq. So we've collapsed that to just a single edge. So in effect, you can think of this equalizer, this pair given by the object E and the arrow eq, as being the a generalization of the solution set of the set of morphisms for which f and g are equal, or the set of values for which f and g are equal. So
wait a minute, I completely don't. Okay, so the point is that I see that single E is mapping both to the X and to the Y. I don't understand that. Say that again. It's the set of.
You've got an equalizer in ordinary algebra, right? So you've got two functions f and g. They're functions on sets. Say the equalizer is just the set of elements x such that f of x equals g of x in y, right?
Okay.
So all we're doing here is we're saying f compose equals g compose eq. Well, that's just, that's saying if we apply f to eq, we get the same thing as if we apply g to eq. So eq is analogous to the set of elements for which f of x equals g of x. So this pair E eq, in the case of functions on sets, contains exactly.
So E restricts us. E
right.
Sort of cuts down the x, basically.
Right. Exactly.
And so, f and g is going to behave the same. That's its role.
Mm-hmm. And again, we have a universal property that's telling us something. That's effectively telling us that E eq is kind of the unique pair for, or the sort of canonical pair for which this works. That any other object O and pair of morphisms, M and N that you could have introduced that would have done the same thing, will have the property that there's a unique morphism from O to E.
So EQ is a solution somehow?
In effect.
Or what's the goal? Where are we heading? I don't know where we're heading.
Well, I mean, so again, like the idea is to have something which in the particular, for the case of set, would give you exactly an equalizer in the standard algebraic sense. So, a morphism, O to X, say, equalizes F and G if it's the case that F compose M equals G compose M. And so E, or eq here is by this universal property, the most general equalizer of F and G.
But we don't want to find EQ. We're not trying to find it or anything.
Well, again, if you were doing a universal algebra computation, you would, right? Because what you'd so if you had a category with difference kernels, so if you're in some category where you can do universal algebra, then the object E gives you the ordinary notion of an equalizer, and equals the inclusion function of E into X. So it's the function that specifies E as a subset of X.
I see. Specifies E is the subset of X for which f of X equals G of X. Is that right?
Which is exactly what F compose eq equals G compose eq means.
I get it. Okay, I get it finally. So EQ E is the subset of X, which is sort of, okay.
Right, so this is the minimal set of equations necessary to define an equalizer, and this is the minimal set of equations necessary to specify the universal property that says this is the sort of canonical equalizer. It's the equalizer so that any other equalizer has a unique injection into E.
Okay.
And I should mention that obviously, in addition to doing just like before with groupoid and commutativity and so on, in addition to reasoning directly over the graphs, you can always request out the sort of algebraic form of what's going on. So you could ask, what are the, if I said span, universal push-out equations or something over here, it would give me the minimal set of equations necessary to define the universal property of this push-out square.
By the way, I assume these equations can be fed into the theorem prover, which will then do useful things with them.
Yes. Yeah. Exactly. Exactly.
Okay.
And in effect, because it's really quite nice the fact that category theory in some sense large parts of it can be reduced to universal algebra, and obviously the theorem prover knows how to deal with universal algebra. So I'm kind of viewing this framework in part as being the skeleton of a general, category theory, type, style theorem prover. That builds.
By the way, I mean, in axiomatic theory, do we have category theory as one of the theories? So that at least with whatever we choose as the final version of the circle dot here, has the axioms of that in.
I don't think so. So okay, unless it's been implemented since I was working on it, I don't think we do we?
Well, then we should have it.
Okay. The reason being, I remember we initially discussed this, and then this is years ago now. And you, Stephen, made some cryptic comment that slightly worried me, which is that you claimed that Saunders-MacLean claimed that category theory is not an axiomatic theory. Which
seems to be nonsense.
Which, well, I thought at the time was nonsense, but I didn't want to. I was
okay.
I was
well, fine. Well,
I
don't know. I mean, it was a very distinct claim, so it was. I think it may have a more philosophical character than we're giving it credit for in terms of the actual structure here.
But I mean, like, there certainly is no limitation to just having, because it's not that dissimilar to say combinator axioms, right? It's just giving you axioms of function composition and identity.
Yes. By the way, what are the central groupoid axioms, and how do they relate to the groupoids we're talking about here? That Mano, looks totally unrelated. Does Mano know what these are?
I don't know how they're related to groupoids and category theory now.
Okay, all right, it's a mystery. Something to figure out. Okay.
They are apparently I've never heard of a central groupoid before. I've found one paper by Don Knuth from 1970 that seems to be about them.
And maybe the name groupoid means something completely different from what it means in category theory.
I don't know. Yeah.
Okay. All right.
Detangling.
Okay. Onward. Okay.
Right. Okay. So what I wanted to show now was the fact that all of these different constructions that seem quite disparate are all essentially special cases of this very, very general construction, in some sense, possibly the most general construction in category theory, which is the notion of a limit. So if I take, let's actually begin with a really simple case. Just to illustrate what's going on. So this is my category. I've just got a single arrow in it. And if I now say abstract limit, this notebook is getting slightly slow, but oh well. I get this thing. So now I can say, do I have to say limit full label graph? No, I can just say that. Right. Okay. So this thing here is what's called, and I should say, so f is a functor, but this could be, and so right now it's just symbolic. This could be any func. I could call it func or something if I wanted to, and I get something slightly different, but let's keep it as f, capital F. So this thing here is called a cone. It's commutative, as with most things. So if I called reduced, it would get rid of that multi-edge. So what this is saying is the notion of a cone is given by, you can think of it as in terms of, you've got a distinguished object L, and you've got L is mapping to f of x and f of y by these morphisms phi of x, phi sub x, phi y, for every morphism f of f that maps from f of x to f of y. Right, so if I had another morphism in here, say that goes from y to z, if I took the limit of that, I'd get a slightly more complicated looking cone.
What the heck? Why is it called a limit?
Well, no, this is just a cone so far. The definition of a limit is a cone with satisfying a universal property. So if I said now universal full labeled graph,
okay,
we get this universal property. So this is now saying that that any other cone that you could, so L is the L phi x phi y is our initial cone, and this is now saying that any other cone n psi x psi y must uniquely factor through L. So in a sense, L is again just like the universal properties we saw before. We're saying that L is somehow the kind of canonical cone, and so when a cone is universal, when every other cone factors through L, or L phi, then we call L phi a limit. And that's what's going on here. And so again, as with most things in category theory, the reason it's called a limit is similar to the reason it's called a push out or a pullback, because these, in the particular case of topology or algebraic topology where they emerged, they are topological limits. So when you formalize your functor as a filter, then your objects are topological spaces, then the limit of that filter is exactly the categorical limit of the corresponding functor.
This is a bit hard to follow for me.
Okay. Well, no, so as I say, the limits are hard to understand because they seem so abstract. But the thing to realize is that basically everything we've just all the constructions we've seen are special cases of limits or co-limits, they're dual. So to see that, for instance, let me take the example of products. So if I said abstract, so you can think of a product as being a limit taken over a discrete category, where a discrete category is one that has objects but no morphisms. So let me define a discrete category. Let's say x1, x2, and it has no arrows. So that's our initial category. And if I now say abstract limit of that, I get the limit of that category. That's the labeled graph, and this is the universal property. And so you can see immediately that this is exactly the same as the categorical product that we saw before. So if I take, okay, so in the case where it had 4 elements, it would look like this. I can see that directly if I go change this to be discrete category with 4 objects. And I would recover precisely the definition of a product. So it's in that sense that we say a limit is that a product is just a limit over a discrete category. In exactly the same way, you could say a pullback is just a limit over a cospan. In other words, a limit over a category that has 2 arrows, or a diagram that has 2 arrows with a common codomain. So if I say f like that, and I take a limit over this, now I get precisely, again, the definition, with some relabeling, I get precisely the definition of a pullback. Or with say equalizers, those are special cases of limits as well, right? And an equalizer for us is just, if we say.
So in some sense, this is a code versus data play. That is, this limit thing is taking what you might have thought of as data, that is the structure of some category, and it is saying somehow that it is encoding certain operations that you have given names to before as being things that you get by applying this kind of universal thing, this limit thing, to the structure of a category. Is that a reasonable way to think about it? And I mean, if you take a more ornate category, well, you get something that is a generalization of, push-outs or something.
Right, yeah, no, exactly. So, push-outs themselves are special cases of co-limits, obviously the dual of limits. But yeah, if you took a co-limit of so a push-out is a co-limit of a span, of a diagram that has 2 arrows with a common domain. If you took a co-limit of some more arbitrary, some more general ornate diagram, you'd get something that was some vast generalization of a push-out.
But so in some sense, this is sort of a higher order function type idea. The
point is, these are all high. Okay, so I agree with the sentiment of what you're saying. So these are all higher level functions, right? Because they're defined by universal property. Even the simplest case, even something like a product is like a higher level function because it's defined by universal property. You're saying this is an operation, and all other operations are sort of special cases. All other operations that with the same arguments are special cases of this operation. That's what that universal property is telling you. Then the limit is the generalization of all of those, where you're saying even that operation is a special case of this very, very general operation, which is taking a limit.
Although presumably there's a family of those things, and you could go and do the next level of this.
No. So limits okay, there are some pretty fundamental theorems that effectively tell you limits are like
universal somehow.
Yeah, as high as you can go in this abstraction tower, that any other universal property or any other operation that you could define by means of a universal property can in turn be defined in terms of limits and colimits. So there's something akin to computation universality that's going on here.
That's interesting. I mean, so in other words, it's ingesting a category, and it's producing this other thing. Okay, that's interesting. Well, okay, don't fully understand, but yes.
Really, it's ingesting an index category in a functor, and it's outputting something more complex. It's outputting because these diagrams involving universal properties are not themselves categories. They're really rules for generate, or they're sort of category schemas, right? Because this is some universal quantifier over all possible morphisms. That's why it doesn't. That's why the thing has dashed lines in it, because it has these universal properties.
So wait a minute. You're saying, okay, I get it. So it's a category schema that has an arbitrary where you as a in some sense a quantified over, or it's a kind of a
no, really. So it's n psi x and psi y are quantified over. You're saying for any object n, and any object and any morphism psi x from n to f of x, and any morphism psi y from n to f of y, it is the case that that there is a morphism from n to L that is unique, and that's given by this thing here.
And why is that the thing that gets to be dotted? I mean, how do you know that those things are quantified over from this diagram? How do you know what's quantified over?
Just because this is the standard notation for universal properties.
I understand, but you said that psi and something else there were being quantified over. How do I tell that from looking at the diagram? I mean, you know,
there's
something
nothing
like
in the diagram itself.
Quantify over the left-hand side and all of the edges from it.
Right, but there's nothing. I agree. Okay, arguably there should be some kind of in these pictures that are effectively showing you category schemas. There should be some kind of tagging that says which things are
one degree of freedom that we obviously have that people have not traditionally have is we can use colors for things.
Right. No, I agree. That would be nice. So, I mean, I should mention the only reason I don't show that is precisely because that's not conventionally how these things are represented.
But I mean, color is a nice sort of piece of metadata we can add in that would be, you know, some eerie color could represent the quantified version, the things that are being quantified over that are not.
Right. So, like, you know, if I show you, like, okay, if the Wikipedia page for limit, for instance, has a diagram of exactly this form. You've got an L, an f of x, an f of y, an f of f, a phi x, phi y, psi x, psi y, and it's only in the text that it says, you know, you're for every other cone, you're quantifying over n and psi, but that's not actually indicated in this picture.
Right. So we need a notation. We need a visual notation for representing that. Maybe it's gray lines. Maybe it's I don't know what. Maybe it's some. Okay. All right. Onward.
Right. Okay. So that's because abstract limit and abstract colimit do loads of stuff, right? They're very, very powerful functions. Most of the other constructions, the things that let you build symmetric monodal categories, dagger categories, all those other things, can be generated using the functionality that I've already shown.
Okay.
So maybe I should now get to at least some of the questions that I kind of wanted to ask design-wise before I proceed in kind of building off the stuff that's already here. There's a bunch of stuff that I wanted to check, just kind of made sense from a design standpoint.
I would say that the first thing is, for goodness sake, let's show this to the graphic design folk. I think we can make these things look nicer. And I also wonder from the graph theory point of view, graph rendering point of view, there's a bunch of places here where where there seems to be an unnecessary kind of exclusion zone around the label, like the N's and L's there. They have a big exclusion zone. And I think, look, go ahead.
Yeah. That's partly by design, because if you just use default graph rendering, you get something that's quite hard to read.
Okay. I suspect that exclusion zone, if there was a light gray background or something in that exclusion zone, the picture will look better.
Okay.
I mean, I think a little bit of experimenting with that is probably worthwhile. But are you happy with the way that the graph layout? I mean, I think the graph layout looks pretty nice in general here. I mean, there are no issues.
No, I mean, you can see I've defaulted to using left to right layout because that just seems like the most natural. it's nice to have all the arrows going in one direction, right? So this is just using.
How did you do that? How did you do the graph layout there?
Just layer digraph. It's using a layer digraph embedding with orientation left to right.
Okay, Roger, do you have any comments on that?
No, I mean that makes perfect sense to me. I mean, that's the option, and then also for readability, I think at least for us that read left to right, that seems natural.
But now layered digraph, does it get confused when you have loops?
Yeah.
And I think we need to look at layered digraphs some more, because we've had an awful lot of things, and Nick has run into this as well, where there are loops and it may not do the, I mean, there are loops and it's not uniquely defined, and it may or may not do the most sensible thing.
Yeah. I mean, if there is loops, it's not a,
I know it's not a layered digraph, right? I understand that, but the question is, since we oftentimes have things that we want to lay out in some kind of layered way, how should we do that? And I think we should probably get some meeting about layered digraph. We should probably get a bunch of examples from Nick and Jonathan and others of things with loops that where it was a question of how it should lay them out. I mean, it doesn't do badly, it does surprisingly decently, but I think it'd be worth understanding. I don't think any of us understand how much freedom there is in laying it out when there are loops, if you get what I'm saying. And we may want to have some extra controls for some of these cases where we're trying to use them for, automatically building diagrams.
Right.
All right, universal limit equations. Oh my gosh.
Just a thing that I remembered. So given we were talking about having good rendering for universal quantification, it would also make sense. I mean, it doesn't do this right now, but if we're going to have explicit quantification over arrows and objects, then when you request out, say, the equations that define the universal property, then these things should have universal quantifier, arguably should have universal quantifiers in them, so that they could be directly fed into the theorem prover.
I would think they should have. Yeah, I would think they absolutely should have. I can't see why they wouldn't have in that case.
Right. So most of the time when you get out a set of equations, it would be just the set of equations, like for groupoid equations or commutative diagram equations or whatever. But for anything defined by a universal property, they would actually have universal quantifiers in them.
Right. I mean, one thing that we still need to probably think through more.
There's probably missing information there, like what is it quantified over?
Well, yes, you have to give that. I mean, one thing that is still a bit confusing for us is the relationship between pattern variables and universal quantifiers. That's a different set of issues. Okay, in any case. So, all right, Jonathan, your set of questions here.
Right. Okay, so a few things, just fairly mundane sanity check things. So we were discussing before that, or at least it seemed to be the case in our discussions earlier, that we kind of agreed just having property names like this is not really rich enough to do a lot of the things you would want to do. So like,
I don't understand why you can't just have property names with, I mean, we've got plenty of functions that have decorated property names.
Right. Okay, but so is that what we want, or do we want to have a separate function that just takes a category and says, give me a list of retractions, or something like that?
I don't know. It's a question of how much we want to bite the bullet and go full category theory, because I mean we'll end up with 30 functions to deal with category theory, presumably, if we do that.
I mean,
anybody got an opinion? Right.
I mean, it would be more consistent with graphs to have a million functions, but I don't know how desirable that is.
I mean, it really depends on how seriously we're going to be able to take category theory as a core feature of the system. I mean, if we can really make it interoperate with practical things, it makes sense. Sorry.
I mean, the thing is, I think there's so many more functions where, this random function with neural networks can return a graph and stuff like that than there'll ever be for categories.
Well, that's the question. Are there places in the existing system? Okay. In the existing system, are there places where we would say, oh, I wish we could return a category from here? For example, in the type analysis of the compiler, there might be places where you say, oh, I wish we could return a category. Is that true, or is that complete nonsense?
No, I doubt it. I mean, there's certainly nothing in the way that the type system is currently set up, where categories would show up.
Next question.
You could probably return something, but yeah.
Right. I mean, next question. Is there a place where we'd like to feed in a category? Is there a function for which it would be nice to say, oh, if we could only feed in a category, that would be useful. Just like there are functions where, like for neural nets, for example, the fact that we have graphs is highly useful for being able to construct a net graph. Are there similar places where it's like just feed in a category? Any thoughts, Jonathan? Any other?
Well, I can only really talk about the areas that of the system I know well, but I think in all of those, there are cases where you might want to input and or output categories.
Explain.
Well, we've already discussed for things like graph rewriting and multi-way systems and so on. Like multi-way systems are interconvertible with symmetric monodal categories. Graph rewritings rewriting rules are interconvertible with spans of monomorphisms. Rewriting events are interconvertible with double push-outs. Rewriting matches are interconvertible with injective morphisms, etc. Similarly, in say the quantum framework, specifications of quantum circuits are interconvertible with string diagrams for monoidal categories. So again, there are cases where you might want to input a category or output a category for those.
What about things like, theorem prover? Explain that one. Yeah.
Well, so if you had, for instance, right, our find equational proof is currently working with an untyped lambda calculus effectively. But if we wanted to do something, if we wanted to have a theorem proving framework that was more akin to Lean or Agda or Coq or something, which was at least simply typed, then there perhaps unlike with the compiler, there you really do want to be able to generate kind of arbitrarily decorated types and functions between them, which are very well represented by categories. So
what's the minimal thing, just so I understand? What's the minimal thing that our untyped equational theorem prover cannot do that a typed lambda calculus theorem prover could do?
Well, so for instance, the thing that Roger was just referring to, right, of like, what are you quantifying over? That's something we can't handle, right? Because precisely for this reason that you're treating the way find equational proof works is you interconvert between universal quantified variables and pattern variables. So we can't define we're quantifying over integers or we're quantifying over thises or that's. Right. So you can say, for all x is an integer implies such and such, and there's a way there are ways you can hack it in certain cases, but there are more general kinds of theorems that involve restrictions of quantifiers and things where that just doesn't work.
Isn't there a second argument for all where you can put stuff like that?
There is.
Like a second of three arguments.
Yeah.
Yes, there is. But that doesn't, the restrictions on the quantification, but the claim, what Jonathan is
claiming, you can say something like, you can say something that's kind of close to that. I mean, philosophically, maybe it's not quite, but like, for example, in the compiler, you often do this with the for all type, which is similar to for all, where you'd say something like, for all of x, comma, x is an element of integers or something, comma, and then the actual statement. And that's sort of a way of just saying that you're quantifying over the integers.
No, sure. I absolutely. Universal, like for all can support this, but a theorem prover based on an untyped lambda calculus definitely can't.
Right.
If you want, even making it compatible, for instance, with the Wolfram language's pattern system would require something internally equivalent to simply typed lambda calculus.
Well, especially if you have slash semicolons and things like that, then you're in dependent type theory and you're going, you're off in crazy land, I think.
And so while the execution semantics for the untyped lambda calculus of the theorem prover is basically trivial, if you wanted even to support simply typed theorem proving, it's suddenly, now your execution semantics is essentially given by some arbitrary category. And in some cases, actually in a lot of cases, it would be nice if you could see what that category is and manipulate it and so on.
So Jonathan, did you perhaps mean that the thing you're quantifying over is like a whole category or something more complex like that?
No, it's not even. I mean, you could have a situation like that if your type structure is given by the category cat, i.e. the category of categories. But no, even something much more mundane, right? So in our current theorem prover, if you want, every function is untyped essentially. If you wanted to have functions that were typed, then then in order to be able to do theorem proving on them, those functions have to be, you have to be able to compose them. And so then the whole type inference system would be given by some arbitrary category, right? Where every object is now a type and every morphism is a function.
Right. Now the type inferencing. So why is the compiler's type inferencing not a category, or is it? But just not very interestingly so.
I think the types are objects in some category.
Yes.
And the compiler, you have practical tools for generating new objects. But you don't say like, plop down a whole category and work with it.
I see. So it's a dynamically generated category where you have type constructors that are extending pieces of, extending out to new objects.
But that, I mean, that itself is a category, right? It just may not be a small category.
Yes, that has arbitrary extensions to it.
Right. But given
that was my point. It's not that you are passing around finite, like complete set like categories as expressed here.
Right. But given a type construct, if we ignore the practicalities of actually of representing this in a finite way, given a set of type constructors, you will be able to generate a category from it. It just won't be.
Well, it's the same story as infinite lists, infinite graphs, all these kinds of things. We can imagine a generator, a schema, but we don't have a good way of representing those infinite objects yet.
Right. So I would argue, until we have a sort of standard way of representing infinite lists, infinite associations, and things, we're kind of limited to only dealing with finite categories.
Do we imagine that we'll be?
The discrete calculus deals with infinite lists all the time. They're called sequences. That's what the whole thing is about. We sum over them, we take products of them, we take differences, ratios, solve difference equations to generate them. They're infinite lists all the time.
Interesting point. But
right.
I mean,
so if you already quantify over objects or morphisms, isn't it already an infinite category if you have an ability to quantify over them?
Right. So in something defined by a universal property, you would be writing down an explicit schema. But that's not defining an infinite category. That's defining an infinite class of categories. That's a different thing.
Okay, but
you still can make a pattern of objects, right? For an object, like if you have a set,
sure,
category, you still can make some kind of pattern.
Right. Just as you could have, right. I mean, this is it's the same discussion we had about infinite lists and infinite associations a while ago, right? The problem is that there isn't a whole lot of non-trivial computation that you can do on those things, and so
you're going to be thrown into set theory, to the general set theory, and so on, where I have no idea whether can our theorem prover this is a general knowledge question. Theorems in set theory, non-trivial theorems in set theory with infinite sets and so on. Can one do any of those automatically, or is that just totally hopeless?
Yeah, absolutely. But it requires a stronger theorem prover than what we have. In
particular, in what way?
Well, because ZFC, there are several ways you can formulate it, but it's either a first order theory. So fine equational proof deals with first order theories, right? Or first order and equational. You can formulate ZFC as a first order theory with axiom schemas, which the theorem prover can't handle. Or you can formulate it as a second order theory without axiom schemas, but one way you can quantify over predicates. And although I implemented like a
the minute you get into higher order theorem proving, I think you're out in.
Right. But like Hall and Isabel and things, can prove non-trivial theorems in ZFC. I mean, parts of forcing have been formalized in theorem provers before.
Do they have higher order?
Yes.
Okay.
Yeah. And like with lean that's based on higher inductive types, you can certainly simulate higher order logics. But you need a richer theorem prover than what we have right now.
But so we can't even do induction, right?
Well, with find higher order logic proof, which is this prototype thing that I made, you can do induction, because you can formulate it as a second order, rather than formulating it as a first order axiom schema, you can formulate it as a second order axiom, but that isn't in system. It's actually
Where
not even, it's not even in the function repository. It's somewhere in the physics project working folder.
We should fish it out. If somebody from project management is paying attention here, let's fish that out and make that a thing. Okay, but anyway, the
I mean, hang on. This is the thing. I mean, I mostly, I don't know why I didn't end up submitting it in the end, but yeah, this is a thing which does. I think I even have an induction argument here. Yeah, right. Here's a higher order induction argument.
Let's get this in. This looks nice. I mean, at least then we have a way to start discussing this issue. All right. Okay, but this is
right. And I mean, the way that this works is kind of algorithmically, it's actually really easy, right? All it's doing is anytime you have a higher order axiom like this one that quantifies over, oh, this is a horrible thing, right? I think I had some meeting, I think Jose and I had a meeting with Adam Strabonsky about how to deal with this problem, that if you put predicates in the quantifier, then the front end automatically strips them out unless you put it in hold form. Which
why
was
does the front end do it? You mean the front end? What?
I mean, hang on, I can
No,
show you.
I think it's just that implies evaluates to true.
Yes, that may have been the problem.
Or no, I thought you were.
There's no front end, Steven. No, the front end is no. This auto evaluation in that case.
Right.
For
sorry.
the condition of for all, is for all hold anything?
Yes, it's hold all custom evaluator.
But for some reason it evaluates its condition.
Custom evaluator means it can do whatever it wants.
Yes, I know, but in particular it evaluates its condition.
Apparently.
Okay, all right. We should look at that because that doesn't seem like it's the right thing. Okay, but it's a separate issue. Okay, let's go back to Jonathan's.
But I should say, all
by the way, the reason it's hold all is to behave correctly is a scoping construct. I think everything else sort of evaluates. So you can't have set. Okay.
I should say that all this is what this is doing is kind of algorithmically trivial. All that it's doing is it's saying anytime you quantify over a predicate, it will just get the list of all predicates that appear in the axioms or in the theorem, and add a single first order a first order instance of this second order axiom, one for each possible predicate. So it's just explicitly like rolling out the predicate quantifier.
It's taking the axiom schema, and it's actually generating an instance of the axiom for every schema element. Is that right? For every schema value.
This isn't technically a schema. You're right in this case that that this particular one is equivalent to a first order axiom schema, but this is actually a second order axiom. And in general, I mean, logicians get a bit finicky about this, but like I think it's the case. So everything that can be done with a first order axiom schema can be done with a second order axiom, but not the other way around.
Fair enough.
Not quite the same, but anyway, yeah, that's the basic idea. You're just unrolling the second order quantifier.
So let's go back to the main design question here. So my feeling is that right now we should have just properties in the category theory framework, because I just think we're going to end up with a zillion functions. I think that, let's start off with properties. It's not going to be incompatible. This is anyway, it's going to be an external, package for now. That will be part of its, if it lands as a system thing in the future, that will be part of its systemization. We'll be making those things into functions. That's what I think.
Sure. Although, as we've discussed, there are particular things like, for instance, abstract groupoid, which I think we agreed would make sense.
Yes, that's fine. That's fine. I mean, I think a modest number of those, mega constructors, so to speak, make sense. But these properties seem to me questionable. Now, in terms of subtyping the retractions, though, subcasing the retractions thing, I don't know what our most standard. Anybody got an opinion what the standard way to do that with properties is? Is it with a list, retractions, comma, and then something else? That seems to be a pretty common pattern for how to do this.
Yeah.
I think that's what we've generally been
Retractions,
doing.
comma F would give the list of retractions of F.
Right.
Something like that.
But then should there be an operator form? Right? Should there be a thing which you can apply to a morphism and get its list of retractions? Or is that too...
Yeah, why not? Why not? I mean, you've got to then given the category, look, you could just have a thing called retraction operator or something, and then that returns a thing that is a function that, when applied to that morphism, it contains inside that function, it contains enough information to know the structure of that category, and then you feed it that particular morphism and it returns the retractions.
Right.
I mean, I don't know what you call that. I mean, it's like retraction. What the heck would it be called? I'm not sure what it should be called. I mean, it's the operator form of finding the retractions.
Right. Retractor. No, I don't know. Yeah. I mean, retraction operator doesn't seem stupid.
It's okay. I mean, that seems confusing because of retraction being, everything's an operator in this world, in this particular zone.
Right.
Let's see. Well, you could call it morphism retraction or something. I'm not sure, because it applies to.
Or, I mean, okay. Maybe in this particular case, right? So obviously retractions are those morphisms that have left inverses. Maybe you could say something. Maybe you could just say left inverses or something.
Yeah, that makes sense. That makes sense. And it gives either you give it like that as an operator form, or it's list left inverses comma A, which would be the non-operator form of left inverses of A.
Yeah. Yeah, I quite like that.
Okay. All right, let's just go on with your list, and then we probably should wrap up soon here.
Right, okay. There are some similar things again about, like, essentially I don't know exactly what level of granularity these functions should act at. So for abstract category right now is a huge function, and it does a huge number of things. And it's same with limit and co-limit. And it's a question of how much of that functionality do we break out into separate functions versus how much of it do we keep in one function.
I would keep it in one function for now, because I think it's otherwise we're going to end up with a much more complicated jungle of design.
Okay. So
the
basic philosophy is keep the minimal number of functions.
I think so. I mean, Roger, Jose, Christopher, anybody got opinions about that? Anybody here? Is that a bad idea?
Well, in general, I think that we should be careful with the names to not preclude the implicit or infinite cases.
I see.
Which you think either this should have a name that definitely conveys that it's a finite thing, or we need to be sure that the design can be expanded later if we want it to be used for both. I was also kind of curious why this can't just be functions that act on graphs.
I think it shouldn't. I mean, I think it takes graphs in some cases to construct things. I think it's great.
Yeah. No, I think it should be its own thing.
I think it's pretty conservative design what you've done now with a few functions. And if we find lots of more applications, more ways in which it sort of connects to all kinds of parts.
Look, I think we're doing, this is the right thing, Jonathan. I think that just like with multi-way system, where it ends up being a function with a giant Swiss Army knife function. Okay, as it becomes a system function, it is going to get cleaned up and simplified once we know, now that we know something about what's important about it. And the same thing will happen here. So I think this is the right way to do it.
Multi-way system is a good analogy, right? Because it has loads of properties, obviously, and loads of functionality built in. But we did break out in the initial release of, for the physics project, we broke out certain things like, causal invariant Q or branch pairs or whatever, as also as separate functions.
Yeah, right. So it makes sense to do that here as well. If there are obviously important functions which are totally obscure to have as properties.
Right.
And I agree that the things like this, I mean, retractions is a plausible, even this left inverses thing is sort of a plausible, because it is returning a function. It's a plausible thing to have as a property. But again, I think we just don't know what, I mean, I'm not even sure that breaking out causal invariant Q and branch pairs was necessarily a good idea, because they're not. There are other things which I might have actually preferred to break out in the end, like things to do with branchial graphs and so on, might have been better to sort of factor out. I think the fact that we factored those out, I don't consider to be a particularly necessary thing.
Sure.
I think they were fine. They would have been fine just left as properties.
Sure. Okay, so a similar thing is, for these very general constructions like equalizer, limit, etc., which are, so, as we've established, these are really like category schemas. Does it make sense, therefore, to have, for instance, for abstract limits, to have an operator form where you get the category schema and then you apply it to a particular category, which is kind of the design I was thinking about for actually instantiating these universal properties.
Well, I don't understand how you get an axiom schema. I mean, a category schema. That thing there is just an abstract category, isn't it?
No, this is the point, right? So again, let's go back to a really simple example. Let's take, say,
no, I got the point that it's not. I'm just asking structurally in the system, what is that? What is the head of that object?
It's abstract product. It is its own thing.
Which is a schema, you're saying.
And so
why don't you just feed it as a subvalue? If you feed it a category as a subvalue, why doesn't that instantiate it?
Well, it probably should, but I mean, okay, sorry, dumb question. What exactly do you mean by subvalue?
I mean, you just say abstract product, of blah, 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 and then of something else.
Well, no, that's exactly what I mean by operator form, right?
Yes.
You would take this, you would say blah of cat.
Exactly.
A concrete category, or an abstract category. That's
what I'm saying. Right, that seems like a very sensible way to do it.
Okay, I agree. I wanted to get that sanity.
Right, even though it is a little bit of a sort of elision, because you could also put in there a property and as a string, but a property as a string is definitely not a category with head, abstract category.
Right, I agree. Yeah, no, okay.
Could you combine abstract product and these other constructions and just use abstract limit? Is there something by having the simpler cases separate?
Well, okay, again, this was kind of this question here, right? Like, so I'm still not entirely decided as to whether it makes sense to have things like equalizers, co-equalizers, products, co-products, pullbacks, pushouts as separate functions, or just have them all be part of these mega limit and co-limit functions.
But basically restrictions on what the index categories you're using are.
Right, exactly, and they come with special naming, default naming conventions and stuff. But apart from that, the only reason I thought it made sense to have them be separate was because all of them are very common categorical constructions. So I felt like there was
but maybe there could be the one function with convenient syntax for all of them.
Right. I'm
like category operation, and then it's what the operation is, for example. Although that's, I think, a little bit of a wimp out.
So like for a product, your index set is a finite category.
Right.
That doesn't seem completely crazy to do that. Although, I mean, one might then ask, why isn't it just category limit, etc.? It depends on how many there are. If you tell me that there are 5, maybe they should be separate functions. If you tell me there are 25, then there really shouldn't. And also, if there are ones that are really obscure, I think it's better to have a string thing, because more like entities then.
Right. I mean, so the ones that are currently implemented as separate functions are the really common ones.
Okay, well, fine.
Or do you really want different representations of the different kinds of cones, and you could pass those in?
That would also be quite a nice way of specifying it.
Also,
I think that would probably be nicer than string arguments, because it's essentially the same operation, like you're saying, but you're giving different input.
Which thing? What are you suggesting?
So product and equalizers, these are limits for different kinds of cones. So it's suggesting maybe we could have representations of the cones.
That's more complicated than I mean, it's more, I don't know the category theory to be able to validate that. I mean, okay, I'd like to also comment, let's see, go back to your list of of issues. I mean, I think this generated variables, generated names thing does need another look, because I think that's otherwise going to.
I mean, okay, and this one, okay, this was in the original version of the agenda, but now I'm currently in the process of rewriting how natural transformations and indeed functors work. This, I think, I've now solved most of these problems. This was kind of a sixth question. So anyway, very soon natural transformations will be back working again, so you can have transformations between functors, and you can reason about, you know, natural isomorphisms and things like that.
What is a natural transformation?
A natural transformation is a structure preserving map between functors.
Okay.
So if you have functors f and g between categories C and D, then you can define you can define natural transformations between f and g. Okay,
general knowledge question. What's the relationship of, you know, mappings between functors, mappings from natural transformations? What's the relationship between that and higher category theory?
Okay, so so you can define something called a functor category, where every object is a functor and every morphism is a natural transformation.
Mm-hmm.
And in the context of functor categories, then this process of building up, you know, successively higher order natural transformations corresponds to higher morphisms in strict higher categories. So that
what do you mean by strict higher categories? You mean in?
Well, strict higher category, like as in not weak higher categories.
What is that? I don't even know what that means. What does weak versus strict mean?
Well, okay, so you know what a higher category is.
I think so.
So you've got, well, so you know you've got one morphisms like, you know, F1.
Yep. Like
this, and then because these two morphisms are between the same objects, I can define a two morphism between F1 and F2.
Mm-hmm.
But I can also have, say, G1. And you also know that there are like two different notions of composition that exist between the two morphisms. So you could have horizontal composition, where you can say now if alpha goes from F1 to F2 and beta goes from G1 to G2, then because the codomain of F1 and F2 and the domain of G1, G2 match, I can compose alpha and beta horizontally to obtain beta horizontal compose alpha. And I can also have vertical composition, where I have something like this. So F1 from X, so F1, F2, F3 all map from X to Y. So I can compose F1, F2 with alpha and F2, F3 with beta. And now I can vertically compose beta and alpha and beta to obtain a morphism, two morphism directly from F1 to F3. Right.
Okay. Mm-hmm.
So both for a strict two category, both the horizontal and vertical composition operations have to satisfy the axioms of a category. They themselves have to satisfy associativity, or at least have to satisfy associativity. If you have a weak two category, then they only have to be associative up to natural isomorphism. And so it's a much weaker. So most of the time, strict two categories are a bit too strict for most of the constructions that you would care about. And what you actually want to do deal with weak two categories. And then this extends when you do this inductive construction. So you go to three categories where you have three notions of, you have, you know, horizontal composition, vertical composition, and some other direction of composition in some third direction, in some third dimension. All three of them would have to satisfy all three notions of composition of three morphisms would have to satisfy associativity either strictly or up to natural isomorphism. So anyway, that's.
I think I need to absorb that more carefully. All right, go ahead.
That brings us on to another question, which is like, there are lots of possible extension. I'm trying basically to get as much of the core functionality implemented and well designed, but once all of this is done, there's no reason in principle why we couldn't support, strict two categories, three categories and so on, and higher groupoids, higher commutative diagrams, those kinds of things. Is there an argument for doing that?
Well, I would say that things that eventually sort of connect to the physics project and so on, I'm highly interested in seeing done. I mean, I think there are 2 points. One is, how does this connect to other parts of the system? and 2 is how does it connect to the things that we're understanding in the physics project and so on. Those seem to be the 2 obvious directions for, I mean, and I think in terms of how it connects to the rest of the system, I suspect that the instancing of categories with specific Fs and Gs and so on, and specific objects in Fs and Gs and so on. Like, for example, Ian, maybe you can say something about how our symbolic work on topological spaces and so on relates to all of this. Could we plug that into this?
Yeah. So if find equational proof or if we had some kind of prover that could handle set theory, then maybe what we did with topology theorems could be like a test suite, like see if the prover can prove these things.
But I mean, in terms of the entities that we've got, could we, these categories, these are abstract categories here, as you've said, but we could imagine concrete things where this is a category of, I don't know, groups, and we're dealing with actual things with particular groups and mappings.
So in that light, like you could say the topology entity store is basically just a bunch of theorems and definitions in the category of sets.
Okay, but can we feed that into this category theory framework and have it conclude useful things? In other words, could we concretify these categories in terms of actual, sets and groups and commutative groups and
what about the category of vector spaces for which we have the morphisms, which are the linear operators, our matrices, and we can check whether they are left invertible, right invertible, and things like that.
Right.
Yeah, the way we would state that a function is continuous in the entity stores was just saying like F is an element of the Hom set for the category top.
Okay.
You just
what Jose
symbolically we just have a named category called top, and then you say things are either objects or morphisms in it.
But so the question would be, in linear algebra, for example, is category theory a useful way to organize certain facts about linear algebra?
Well, I mean, this is the point that I already raised in relation to the quantum framework, right? So there you have exactly a concrete category equipped, it's a category equipped with a functor to FD Hilb, the category of finite dimensional Hilbert spaces. And then you've got, then you're in the domain of doing categorical quantum mechanics. And then, in the same way, if you have a way of representing symmetric monoidal categories and string diagrams in those of those symmetric monoidal categories, then if you have an abstract category with a faithful functor to vect, the category of vector spaces, then you can do diagrammatic linear algebra, which is its own thing.
And that's tensor diagrams, is that right?
Right. So tensor networks are a special case of monoidal string diagrams for vect.
Okay. I mean, that's something that we've been independently interested in with respect to sort of our generalization of array operations. I don't know, does anybody here know about that? We've had that in a, we were talking about that. I mean, threaded is our first adventure in terms of that kind of thing, but there is a belief that there's more that we can do in terms of general. Jose, do you know about that? This I mean, we're talking about tensor diagrams as a way to generalize what we're thinking about with arrays, or am I confused here?
I don't know of a connection with category theory. This is very abstract for the sort of thing I usually deal with.
Fair enough. Okay, we should probably wrap up here. I see some comments on our live stream from RBS asking why are we using that circle dot for composition? Yeah, we discussed that earlier in the stream. That we don't really want to use that. We want to use something simpler. We would like to use the pure function composition thing, but that will evaluate, and we got some problems with that. And it's kind of a symbolic version of that, formal version of that we need. It's a question which I don't understand from Universe. Can groupoids be nested? I don't know even what that question entirely means. Is there an obvious answer to that question, Jonathan?
I'm not sure I understand either.
Okay, all right, fine.
I mean, you can certainly, with any categories, you can glue these things together, right? You could, and so you can in effect do the analog of recursion on categories if that's what's being asked.
Well, I guess this category schemas, I do wonder to what extent they can be thought of as categories with blanks that are, I mean, to what extent are they like lambdas of categories, and to what extent are they like categories with blanks and so on?
Well, in effect, I think they're exactly like categories with blank, or in a sense, like something like this N is just sort of anything that matches. If we imagine having a pattern object, this is just matches that pattern, right?
Yeah, which suggests that maybe we should treat these category schemas as things with pattern objects in them instead of literal objects for objects, literal objects as objects, pattern objects as this sort of schema objects.
Right. Which is, again, implicitly what we would be doing if we included for alls and we did a theorem prover version of this. Yeah,
except that the relationship between for all and pattern variables is a little bit obscure.
Well, not for the untyped lambda calculus of the theorem prover. They are the same.
Right, I understand. Comment from RBS about similarities to graph theory. Yes, in the earlier part of the stream, Jonathan showed that this thing can eat, all this category theory stuff can eat, graphs, and you can apply graph operations to these categories. In fact, I bet if you say simple graph, what would happen if you did that to that one there? Percent.
Yeah. Simple graph. And in general, if you take I mean, that thing there was not a category, it was a category schema. But in general, if you take a category, like, I don't know, this, category 3, and you say, rather than reduced labeled graph, you say simple labeled graph, it will strip out all the multi-edges and the, category 3. It will strip out all the multi-edges and all the self-loops and just return the simple graph.
Right. It is very nice that these tagged edges work so smoothly with this. I mean, that you can then just do pure graph operations on these things. You can, can't you? I mean, they are there. If you look at what that thing is, it is just a graph with tagged edges. Is that true?
Oh, yeah, absolutely. And as we discussed earlier, and as Roger kind of brought up earlier, essentially all of this kind of fancy universal algebraic stuff that we're doing, most of it just internally is done with graph operations.
Which
the actual algorithmic lifting is just graph theoretic.
Which means that we can scale up to industrial size finite categories, which is nice. I mean, where are those used? Giant, other than in the physics project, where we have like mega sized categories. Where else do people use industrial size categories?
I mean, like I say, in most actual category theorists will be dealing with non-small categories.
Yes.
You mean something different?
Well, I mean people who use category theory as an organization scheme. I mean, like the people who are doing sort of chemistry-related category theory, like that, the Kappa people and so on. What do? Don't they have finite categories, don't they?
Yeah, right. Or at least okay. Generally, in those kinds, so with things like CatLab and Kappa and all other things that use category theory as the underlying formalism for some larger computational framework, most of the time what they do is they have a formal semantics that involves non-small categories, but then they claim that at any point in time you're only ever reasoning about a finite subcategory of it.
I see. I mean, and then there are these things to do with data validation and so on that use category theory, although this seemed like not totally convincing and really using some kind of type theory instead. Is that true, or is that
right? Although, I mean, a lot of the time the theorem provers that are used for kind of verification of typed functional languages, very often they are category theoretic in nature.
Like what?
Well, I know that like a bunch of the type checking in GHC, for instance, in the Glasgow Haskell compiler, is effectively uses compositional theorem proving techniques.
What is compositional theorem proving?
Well, I mean, theorem proving that uses sort of the framework of category theory.
And of the theorem provers, which ones do that? I mean, there are ones that are. When you say, go ahead.
Well, because of Curry, Howard, Lambeck, any theorem prover that uses that uses at least simple typing will everything in that theorem prover will be interconvertible with something to do with categories.
Yes. Okay, but I'm still not. It'd be nice to know what is there like an obvious killer theorem which needs typed lambda calculus to prove it? Since you said ordinary induction can be done a different way.
Yeah, although I mean this is far from efficient.
Mm-hmm.
I mean, just as it's.
I mean
it's
that theorem prover. What was the theorem prover? The one that the Boyer-Moore theorem prover thingy, wasn't that an early? What's that?
Which is now called NQTHM, I think.
Okay, but I mean that theorem prover was specialized in induction kinds of things, if I remember correctly.
Right. Yeah, I think that's right.
But okay. Well, this looks quite lovely. I mean, really looks great. I think, again, just as a practical matter, let's get some meeting to just look at the graphic design of this. And let's, I mean, it looks to me like if you have a comparatively modest number of functions, what is going to happen implementationally? Is this going to be a packlet that exposes itself through the function repository, or what?
I think that makes sense for the moment. So right now we have on the framework, all told has on the order of about 20 functions. I may be able to simplify some of that.
Okay.
And so it seems like the best thing to do is, yeah, as you say, have it be a packlet repository thing with exposed things, with exposed stubs in the function repository.
Sounds sensible to me. Anybody else with any other comments on this?
Just would have been really helpful when studying these things in grad school.
It looks good. It makes it, I think it will be helpful for a lot of people to understand it. Now we have to make this framework, and then we can make a little course around it, so more people can actually understand this stuff, including people like me. Anyway, okay, good. All right, thanks very much, and thanks to everybody.